Welcome everyone. Welcome to Accelerating AI 2023, Challenges and Opportunities in Cloud and Edge Computing. I am your host. My name is Yassine Hariri, and I am Staff Scientist, AI and ML at CMC Microsystems, and I work with the IoT and Edge AI group. So first of all, I would like to welcome you and welcome our distinguished speakers for accepting the invitation to participate in this workshop. I would like to mention that the session is recorded. So this is an annual workshop. This is the fourth time CMC hosts Accelerating AI. And the main goal here is to bring experts from industry and academia to, first of all, share the latest trends and innovation in the space of AI, identify challenges and opportunities, explore collaboration opportunities, and identify common infrastructure requirements. So the topics in this year's workshop, our distinguished speakers will be delving into a variety of topics related to machine learning and artificial intelligence. These include practical applications like computer vision, natural language processing, and EDA. We'll also be exploring novel hardware options such as GPUs, FPGA, and custom accelerators, as well as software stack that support these technologies, including libraries, compilers, ML framework. Additionally, we will be discussing ML benchmarking on emerging AI hardware. So just a high-level overview about the agenda today. We have a very busy agenda, so we'll start a presentation from CMC Microsystems so a brief intro of CMC and also some high-level details about key trends in AI acceleration. Rick O'Connor from Open Hardware Group will be covering open source RISC-V course for industry and academia. And our new partner, Entity AI, where Gaurav will be presenting energy-efficient AI inference acceleration with Entity AI technologies. We have Griffin from NVIDIA, who is a long-term contributor to this workshop, and will be presenting acceleration of transformers with FP8s. We have also a presentation from DeepLight, who are specialized in optimization of AI network, and Davis will be presenting running 2-bit quantized CNN on ARM CPU. We will have a quick break around 2:30, and we'll resume the workshop with a presentation from Professor Andreas Moshosov from University of Toronto, who will be covering software, hardware, innovation in the space of AI for training and inference. Then Warren, also a long-term contributor to this workshop from McGill University, will be presenting standard deviation-based quantization for deep neural networks. And we will have a presentation from Nizar from Polytechnique, who will be giving some updates and details about a large collaborative project involving CMC and the Open Hardware Group and colleagues from ETH Zurich, a RISC-V multi-core vector processor. And we will conclude the workshop from Professor François-Ludic Primo from Polytechnique, who will be presenting designing robust DNN models that exploit energy reliability trade-off. We will have an open discussion around 4, and we'll be concluding the workshop at 4:30. Sorry. So a quick intro about CMC Microsystems. So we are not for-profit organization dedicated to accelerating research and innovation in advanced technologies. And since our inception in 1984, we have been committed to reducing barriers to technology adoption by creating and sharing platform technologies, providing access to state-of-the-art design, manufacturing, and testing capability. We offer a range of services to simplify access and reduce the cost of advanced technologies in microelectronics, photonics, IoT, and Edge AI, MEMS, nanofabrication, and integration, as well as quantum technologies. So our independence from any specific application means that our services are equally valuable to those engaged in advanced manufacturing, clean tech, agriculture, health, and beyond. And we offer the necessary infrastructure and work to reduce barriers to the adoption of cutting-edge technologies, empowering our users to conduct research with greater ease and efficiency. We take great pride in sharing success stories of researchers who have utilized our products and services to develop innovative technologies. And these success stories often highlight how our solutions have facilitated the creation of spin-off companies, demonstrating tangible impact of our offering. We are proud to be part of a Canada-wide collaboration between 68 universities and colleges, connecting 10,000 academic participants with over 1,000 companies to design, make and test micro and nanosystem prototype. And through the collaboration, we enable innovation and skills development for HQP, benefiting 9,700 HQP to date. Our efforts also have resulted in over 400 collaboration with industry, thousands of publications, 125 awards, 65 patents, 8 new startups this year, and 820 trained HQP who moved to industry. Our products and services can be grouped in 3 categories: CAD, Fab, and Lab. CAD consists of state-of-the-art software for successful design. Fab simplify access, reduce costs for working prototype, and Lab provide tools for test and demonstration. So as conclusion for CMC introduction, currently Fabric is a proposed 5 years, 200 million project led by CMC Microsystems and 13 other founding organizations. And this is the first of its kind national ecosystem to create critically needed semiconductor capabilities in Canada. So it's one project with 5 main activities. The first one is to ensure or create capacity for fabrication of semiconductor devices in Canada. And second goal is to accelerate R&D for IoT products and services by SME operating in all verticals, and develop HQP and take quantum technologies to market and grow Canada semiconductor ecosystem. So now some high-level AI key trends that I would like to present in order to set the stage for the rest of the workshop. So as you know, in recent years, we have observed a significant trend in the convergence of IoT, AI, and 5G technologies. And as a result, there has been a surge in demand for power-efficient, secure computing at the network edge. And as these technologies continue to generate vast amounts of data from sensors in wearable, biomedical monitoring devices, autonomous driving systems, and precision agricultures. However, this growth of data combined with the exponential rise in AI and ML complexity has created a pressing needs for new computing architectures and system integration technologies to address these emerging challenges. Some economic data here. These charts depict the significant impact that AI is anticipated to have on the IC chip market's growth. And this is showcasing a projected 32% increase in market size by 2030 due to the AI value contribution. And in terms of AI chip set revenue by market, the revenue generated by AI chip sets is largely dominated by consumer electronics, industrial, and automotive, although we see also some increase in the biomedical space or healthcare. By type, AI chip set revenue can be categorized by type, including GPU, CPUs, FPGA, and ASIC, and others. And during the forecast period, the ASIC segment is predicted to experience substantial growth due to its use in high-speed performance processors such as Google Cloud TPUs and Edge TPUs. And additionally, FPGA remains a major accelerator type, having been adopted by key players such as Intel and AMD. In terms of the AI hardware, in 2x2 matrix, you have the cloud and the edge, although we have various level of the edge, and training mostly happen in the cloud because of the big size of the models you are dealing with. So you need a lot of compute power and compute storage. Inference happens in the cloud and at the edge. And as a major trend, we see a lot of migration of applications to the edge, which require more innovation in the AI hardware for edge deployments. This is confirmed by this projected slide, which shows that by next year, more than 60% of the devices will be AI enabled. So more than 60% of the devices, either in consumer electronics or in healthcare, will have some AI capabilities, and this trend is to continue. So this is a summary of what we have observed over the last few years in the edge AI environment. So definitely there is a migration of AI workload to the edge. And the advantages is low latency, bandwidth saving, connectivity, data privacy and security, autonomy and reliability. And this increase demand for edge AI hardware that balance performance, power, efficiency, and cost, creating opportunities for domain-specific general purpose smaller processor units, and these are type of processor that can deal with large or variety of, for example, CNN or transformers. And this requires innovation at all hardware stack, including complex multi-level memory hierarchy, massive multi-level parallelism, highly efficient ML mapping tools that deal with the increasing complexity of the software. We have also noticed the emergence of non-conventional architectures such as quantum computing to accelerate training and spiking neural network and analog computing. In terms of the risk and uncertainty, we all know that Canada has excelled at AI software thanks to the three major institutes, Mila, Vector Institute, and AMI, but it risks lagging on innovative edge AI hardware. So there is a gap there, and one of our objectives at CMC is to enable the next generation of innovators in the space of AI hardware by providing the necessary infrastructures and tools and support for that. So the challenges, the technical challenges is the increasing complexity and continued innovation in AI algorithms, high computational complexity, small memory footprints, low power consumption, and you need highly efficient mapping tools and trustworthiness, which combine safety, security, resiliency, reliability, and privacy. So these are the challenges facing the migration of AI workload to the edge. In terms of figure of merit, and this can change every 6 months. So there are a variety of edge devices, from smart devices, vehicle edge, and edge gateway. And although these numbers shows some figure of merit from a marketing point of view, but I think there is a need to focus more on meaningful figure of merit, such as inference per second per millimeter square, inference per second per watt, and bandwidth per inference. This slide just shows some use cases of edge AI application. So from on-device inference to which use, for example, face detection, to augmented reality, to autonomous driving. And each one of these applications has its own power and performance budget. In terms of training, we've noticed explosions in terms of the number of parameters required to train a large neural network. And the main trend is that in the past, we faced challenges with data-bound models where the focus was on finding ways to feed accurate data into these models to train them efficiently. However, things changed drastically. We are now encountering a new set of challenges known as compute-bound problems, and this means that the computational resources required to perform certain tasks have become a limiting factor, and the transition from data-bound models to compute-bound problems is significant, and it's clear indication that we need to shift our focus toward finding more powerful computing solution to tackle these new challenges. So in terms of what CMC offer to support the space of AI ML, so we support an advanced AI ML infrastructure powered by leading edge accelerators such as GPUs, FPGAs, and NPUs, along with technical support and training for edge AI. And the main goal here is to enable researchers or users to easily and seamlessly build and optimize and deploy their model from the cloud to the edge. So this is a short introduction from CMC, and now I will go back to the agenda, and I will present our next speaker. Rick is the founder, president, and CEO of the Open Hardware Group, a global not-for-profit organization where hardware and software designers collaborate on open source projects. He previously served as the executive director of the RISC-V Foundation, which is founded in 2015, with many years of executive level management experience in the semiconductor. Rick possesses a unique combination of business and technical skills and has been responsible for the development of numerous successful products. Over to you, Rick.
Great. I'm hoping you can see my title slide.
Yes.
Good. Thanks, Yassine, and hi, everyone. Appreciate the opportunity to be part of this workshop. Thanks to the team at CMC for inviting me to give a talk. And certainly the intro you gave, Yassine, where the Open Hardware Group ecosystem fits in, as you had on that second last slide, I think, or your last slide. You know, the Core 5 family of open source RISC-V cores is an interesting set of building blocks or an enablement for customized compute at the edge, embedded class, be it like deeply embedded captive cores attached to accelerators, or SMP Linux capable cores. So my talk today is to give the attendees an overview of what the Open Hardware Group ecosystem is about. As Yassine said in the intro, I started the RISC-V Foundation. Started hanging around with the guys at Berkeley back in like 2013 and started the RISC-V Foundation in, I guess it was late 2014. And we incorporated that nonprofit in summer of 2015. I grew that organization to about 400 or 500 companies and left to start the Open Hardware Group, which is a nonprofit ecosystem for generating open source artifacts at the RTL IP block level. So this is a federally registered nonprofit corporation in Canada. We're also registered in Europe, and the intent is to have a global ecosystem with no geopolitical influence, footprints around the world with many developers, sharing the collaboration and a distributed engineering workforce, if you will, collaborating on the development of RTL, verification, development kits, OS porting, software tool chain, everything you'd expect to see that in terms of what would come along with a processor IP core from an enablement standpoint, coming from an open source contributed engineering development community. So that's what the Open Hardware Group does, and I'm just going to show you a little bit of the size of it. So we have about 104 member companies and partners at the table, lots of industry participants, many logos I'm sure what you'd recognize, lots of strong academic participants, again, many logos what you'd recognize, and CMC has been a strong supporter of the Open Hardware ecosystem from its inception, so thank you to the CMC crowd. And then lots of partners helping us curate this IP and bring it to the ecosystem. So across these 104 some odd companies, the organization is structured in a series of working groups and task groups. You should think of this ecosystem as a cluster of about 400 to 500 contributing engineers from around the world, all with their own compute and CAD tool capabilities in-house, by collaborating publicly in the public domain on the Open Hardware GitHub repos. There's roughly 23 projects, I think, that are in flight right now. Obviously, not every one of the 400 or so, 500 engineers, the different member organizations participate in every single one of those projects. Each company or organization has their own project interest. But the point is, it's very active, developing a family of open source RISC-V based processor cores. And the way that we're structured with those working groups and task groups, I'm going to talk about two key task groups for this discussion. There's a heck of a lot more detail to share that takes way more than 15 minutes, but I'm going to talk about two task groups here this afternoon. One is the cores task group, which not surprisingly looks after the family of cores. And we got started in life with the contribution of two cores from ETH Zurich, Professor Luca Benini in Zurich, Switzerland. If you're not familiar with ETH Zurich, it's basically the MIT of, if you will, of Europe. It's Albert Einstein School. It's always ranked in the top 10, if not top 5 engineering schools in the world. It doesn't get a lot of airplay in North America, but it's a very prominent and large engineering school. And the RISC-V core, as they had named it, and the Ariane core are two cores. This is all system Verilog based stuff. The branding or naming convention that we've adopted is CV for Core 5, E for embedded, and 4-stage. So think of that as like a Cortex M4 class if you are familiar with ARM cores. And then CVA6 is an application class core, Linux capable core, 64-bit engine with a 6-stage deep pipe. And you can sort of think of that as any 53 class core. And that's how we got started in life a few years ago. And that's translated into 9 different cores. This is a bit hard to read, but if you'd rather go to the GitHub repo right now and start playing, just go search for OpenHW group in GitHub, and you'll see the landing page where this roadmap is, with a table of contents linked to all the different repos and projects that are underway in the ecosystem. Here's a slightly larger view of that roadmap. I'm assuming my slides are advancing for you, and I'm just carrying on, so interrupt me if they're not. Slightly larger view of the roadmap, set up into 2 different categories, a number of different variants on the embedded class side. So many of the E4 family variants, as you can see there. There's also an E2 variant down there. Think of that as an M0 plus, if you will, 2-stage deep pipe. And then a few application class cores. In the CVA6 box, or row at the top, there's actually 4 different variants of that core that are in flight right now, and a lot more detail underneath, all this work. So part of the activity is not just the RTL for the cores themselves, a very active verification task group generating a system Verilog EVM-based test bench to verify all of these cores, and have industry-grade verification, coverage-driven verification, with code coverage, assertion coverage, FSM coverage, to verify the cores and then freeze that RTL to have these cores available for use in high-volume production SoCs. The first entrant, the original RISC-V core, is this guy here in the E4 class, the V1 version of that core. We froze that right at the beginning of 2021, and there's roughly about 100 million of those cores in production now, and entirely open source, permissively licensed, no royalties, way you go. It's pretty cool ecosystem. This is the block diagram of that core. Pretty simple 4-stage store embedded class core. All of the production use so far is entirely captive. So these things are attached to something else, or a programmable FSM, if you will. And I'll show in a few slides an SoC that the CMC team is very involved in, that has an embedded FPGA array attached to the core, so you can attach your own accelerator and use that as an experimentation platform. So the way to think about how the ecosystem can help you with AI and ML applications is some very basic compute building blocks, if you will, that you don't have to spend any time doing anything with. And you can just leverage and add your own secret sauce. If you're not familiar with how the RISC-V ISA is structured, there's a reserved area of the instruction set architecture for user-defined opcodes and user-defined instructions. So you can tailor your own purpose-built accelerator and stitch it right in to the pipe and have those instructions dispatched off to your accelerator, and away you go. So on the 64-bit side, so this is the Ariane core, as it was called back at ETH. A very simple single issue in order 6-stage core, capable of building into a coherent cluster, running SMP Linux, and very, very active. Both of these cores have probably seen different tape outs to the tune of around 40 different tape out designs each. And as I said earlier, the E40 or the E4 core that I was talking about is close to 100 million in production now. So beyond the cores, it's great that you got cores where you're going to, they need to be verified, they need to have tool support, but we need to have physical implementations either in the form of FPGA emulation or real SoCs. So we're thrilled to have Hugh Pollitt-Smith from CMC chair our hardware task group, and this task group is basically an internal customer, if you will, within the ecosystem, taking the output from the cores and the verification of the software teams and building SoC and FPGA implementations and development kits underneath that. So I'll show you some of those examples. We're partnered with Vigilant, so we use really two platforms from them: the Nexus A7 and the Genesis 2 FPGA platform. Those are both Xilinx-based boards to have early bring-up environments and execute hardware emulation for these implementations, and have an Eclipse-based IDE called the Core 5 IDE that is contributed by Ashling. So it's quite a healthy development environment and bring-up environment for these platforms. And this is one of the tape outs that I was referring to. So this is a 22 FDX-based MCU. Global Foundries is a member of this ecosystem, it has the E40 core here in the middle, an embedded FPGA array from QuickLogic, and then a whole series of generic vanilla flavor peripherals. We have handed off the GDS2 database. The great team at CMC has handed off the GDS2 database to GF, and we should get silicon back late July, early August. So we're very excited about this. And that's going to get turned into our first development kit. We've been selling these into the ecosystem on a cost recovery basis. There's a group gets campaign page that's up. We'll be announcing pricing and availability for this kit here quite shortly, but you can go either to the Open Hardware Group site, and there's a link at the top called Open Hardware Dev Kits or Core 5 Dev Kits, or you can look up Group Kits and Core 5 MCU, and you can get on that campaign page, the mail list, if you're interested in getting your hands on one of these guys. And then on the 64-bit side, as I said earlier, the CBA6 is a Linux-capable 64-bit application class core, and the team at Talus is very active in leading the developments around this core. And in addition to what I showed you with the block diagram earlier, we have a healthy contributor ecosystem. The hypervisor extension is being contributed by a development group. There's very active work at integrating a vector accelerator, and we'll talk about that in more detail, with a project that CMC is sponsoring into the good team, Mimosa Adias team at Poly Montreal, and you'll hear Polytechnique Montréal, and you'll hear some more about that later in a few minutes, and I've got some slides on that. So there's lots of activity around the 64-bit core, including U-boot Linux-based with a Yocto project. Now you can run FreeRTOS on the core. We have a dual-core SMP version. So this is a dual-core 64-bit cluster using the coherent NOC called OpenPython or PMesh that originates out of Princeton, running on the Genesis 2 platform from Vigilant. We have a 16-core cluster that runs on a Stratix 10 board, again leveraging the OpenPython coherent NOC. Very cool. And then this is a great project that got started a couple of years ago. You're going to hear from Nazar later in this talk this afternoon, where he'll talk about Polera, which is the SoC that integrates this work. So CVVec is a 1.0 RVV 1.0 spec compliant vector accelerator, RISC-V vector accelerator that attaches to the 64-bit core. The project sponsored by the team at CMC. The ETH Zurich contributions are led under the guidance of Frank Arcagnac and Mateus and Mateo. You can see here. You'll hear from Nazar under Yvonne's team, and there's a bunch of other great folks involved, like Hossein and Johan and Elizabeth and many others. And the team at UC Santa Barbara is actually the team that's contributing the OpenPython mesh. Jonathan Balkan did his PhD research work at Princeton, and he now has his own lab at UC Santa Barbara and is continuing on with that work, and that's how they're involved. So what this thing is a quad coherent cluster of vector-enabled 64-bit SMP Linux capable cores. This is what the Polera device looks like with the 4 tiles with each of those compute engines. And the expectation is that we'll be taping out, well, hopefully within a few months, and the team is working hard to do that. And again, we'll have development kits that we'll build around this and make available to the ecosystem. That's the end of my talk. I'm not sure how well I did with leaving the time for Q&A. I'm hoping that there's some time, as I won't be able to stay for the whole day. So if there's questions that I can take now, I'd be happy to do so.
Thank you, Rick, for this great presentation. If you would like to ask a question to Rick, you can either unmute yourself or ask a question in the chat. Maybe I can ask a very intriguing question. Is based on your experience in the open source world and taking open hardware RISC-V as an open source, what is your main 3 big challenges in bringing the ecosystem together to collaborate and to maintain these cores?
3. Well, I'll tell you the top one. Open source is a collaborative effort, or in order for it to be successful, it needs to be a collaborative effort. You and I could work on something. Hey, go pick up the RISC-V ISA specs. Say, develop our own little embedded class core, and say, flip that up on GitHub, call it open source, and hope the world likes it. And more than likely, that's going to die on the vine. Being able to assemble a community that actually works with us in the development, works with us in the verification, and then there's a path to readying that IP for high volume adoption commercially. That's how open source succeeds, right? So I've given a number of talks comparing the evolution over the last 20 years of the open source software industry and the business that needed to exist, and commercial adoption that needed to exist for that hockey stick to actually happen. So creating the pull from industry and the engagement from industry with an eye to adopting these open source artifacts, and then the confidence from those large SoC companies that they can use this IP. It's well verified. They know where it came from. There's an ecosystem behind it with critical mass. Those are some of the key building blocks, right? So that adoption ecosystem, high quality verified cores, and then commercial ramp, right? Those are the 3 probably significant barriers to growth in the open source hardware domain. And hopefully it doesn't take us 20 years as a hardware industry to achieve what the software industry has achieved now.
Thank you, Rick. Any other questions from the audience?
Trivial question. I'm assuming, Yassine and Rick, that these slides are going to be available after, because some of the pointers I'm discovering things, Rick, that I didn't know about, some of the aspects of the technology you're offering. Some of the thing on FPGA would be very nice for some other projects.
Okay, perfect. Yeah, of course they're available. Yeah. And it's always good if you knew everything I was going to talk about, then my talk wasn't that interesting. So that's good.
Great. Thank you very much. Thank you very much, Rick. And we will switch to our next speaker, Gaurav. Can you please share your desktop?
Yeah. Let me try screen share.
So Gaurav is the Director of Technical Marketing at Entether AI, and he will be presenting Entether and talk about the latest developments. And prior to Entether, Gaurav spent 5 years in the autonomous vehicle industry, first as machine learning researcher and then later in the business strategy group, all at Ford.
So let's stick to the title slide for now. So hi everyone, my name is Gaurav Singh from Entether AI. And I would like to introduce you to our products at UAI. We call it UAI in short. So we'll be specifically focusing on Run AI devices, which is our current generation of AI inference acceleration device. And there's an Imagine software development kit, which is associated with Run AI devices. So Imagine SDK gets you from a trained machine learning model to an optimized model, which can run on Entether AI's Tsunami PCI Express Gen 4 cards. So Run AI is a chip name, Tsunami is the board name. And what we have at CMC server is a Tsunami 200, which is a Run AI 200 chip on a board. We also have Tsunami 800, which is 4 Run AI 200 chips on a board. We'll show you all of that in coming slides. But at the bare minimum, like if you go at the minimum, Run AI 200 chip provides over 500 operations per second of integer rate operations. And it has like inference performance and can support up to inference efficiency of up to 8 TOPS per watt. So on this slide, we are trying to explain our motivations on why we are doing this. So there are 4 key issues we are trying to address. This is what guides us in developing this architecture. Our first is the changing AI workload. So many neural net architectures are coming up, taking on diverse applications. Like you take a 2 weeks long vacation, you come back and you're already behind. So many new AI papers and tools, and it's just too much to go through it. So our solution is that we make an architecture which is flexible and programmable so that you can keep up with all the new AI stuff which is happening. Second is the scalability. Right now, a lot of people are training their models, but eventually they have to deploy it. And still inference is happening in the cloud. And that won't scale because eventually people will want lower latency and higher bandwidth. And for that, you need to move on to like more edge devices and an architecture that scales. Third is the efficiency and performance. So obviously, you probably have heard this, 1% of worldwide electricity usage is happening in data center. And this data is from 2021. So there was no ChatGPT back then. Now it has gotten worse and it will go up to 15% due to growth in inference deployments. So what we are looking for is an extremely power efficient architecture. And lastly, a lot of inference devices, we look at them, how they work is that they try to dequantize. So what it means is that they go from like integer float 32 to integer 8 and so on, and then they lose their accuracy. So, and they're like analog inference devices also. So our plan is to like keep the accuracy as much as possible. So support the right data types and use advanced quantization techniques so that we don't lose accuracy. So next slide, please. So this is our unit device, which is like, this is the first device we came up with. So what it does that each chip has 200 megabytes of on-chip SRAM, and that is why it's called Run AI 200 because it has 200 megabytes of SRAM. All of that is distributed across 511 memory banks, which we will talk about in next slide. Each memory bank has about 512 processing elements, about 250,000 Ps, 500 TOPS of performance. With 75 watt TDP, you get about 8 watts, 8 TOPS per watt average. Inference is focused, so it's very optimized for like INT8 data type. We have 2 modes. One is called eco mode and one is called sport mode. Eco mode is that when we want to like minimize the power consumption and like minimize uh, energy loss and maximize the efficiency. And sports mode is when we want to maximize the performance, so like maximum throughput. So it's TSMC is 16 nanometer, 18.4 billion transistor, die size is 47.5 by 47.5. And it's all connected through PCI Gen 4 and 16. Next slide, please. So our approach, how did we come up with this, is that when we were looking into this back in 2018 when we were founded, so we recently celebrated our 5-year anniversary. Most of the energies when you are training your model is being spent to run functions in processors. So it's like a lot of data movement is happening and that is consuming a lot of energy. So for example, in one human architecture, the data goes from like RAM to cache to pipeline logic and ALU. And that's using up about 2.5 petajoules per B per byte. And look at that, the 90% of that is happening only through all the transportation. So going from local SRAM fetch to DRAM fetch transport. So 90% of that can be avoided if we use something known as at-memory computing. So our co-founder, Martin Snellgrove, has been working on this at-memory computing for about 3 decades now. And what he has done is that he has put memory very close to the processing elements in all our architecture. So we can go on to the next slide. So yeah, so if we reduce that, if we reduce the data movement, we get rid from like 6x reduction. So instead of 2.5 petajoules, we go to 0.43 petajoules. And that is our goal, to like minimize data movements by putting processing elements close to the memory so that it just consumes less energy. So can we go on to the next one? So I have given a comparison of 3 architectures that are commonly used. Near memory one human architecture is what we are familiar with. It's very standard, industry standard. And then we have in-memory computation, which is multi-value memory cell. There's analog techniques, a lot of support circuitries. But what we are is in the sweet spot. So we are at memory computation. So we have short, massively parallel connections. We have about I think hundreds and thousands of these processing elements are in a single chip, and they are massively parallelized. So since we built our architecture around inference itself, we are bolting the memory directly to the processing elements. And that is, the processing elements are basically multiply and accumulation. So all of that multiply accumulation is happening and then getting stored at the same place. I have a detailed slide, I think, on probably next slide, where I discuss how it's actually work. Yes, that's the one. So this run AI architecture is very spatial architecture. It has direct row transfers of column-based bank-to-bank connect through 32 gigabytes per second. We have pipeline bus, so it's row-based ring. We go 8 gigabytes per second per row. All the connectivity to all the memory banks. So these small pink ones are called memory banks, and there are 511 of those. All of these are connected to host through a PCI Gen 4 32 gigabytes per second. Each of the memory banks also contain memory. That is what I mentioned about like bolting memory itself at the processing element. So each memory bank has 385 kilobytes of SRAM. If you multiply 511 by 385 kilobyte, you'll get 200 megabytes roughly. And each memory bank itself has 512 processing elements. So if you multiply 500 by 500, you get about like 250,000 processing elements. And it's a RISC controller. It's row-based bank-to-bank local interconnect, 16 GBs per second bank-to-bank, and total of 8 terabyte data transfers per second. Next slide, please. So this is all about hardware. Obviously, nothing in this modern world. Hardware doesn't mean anything if there's no software. So we have developed this software development kit, and we call it Imagine. And what is does that? The SDK is basically, let's say you use NVIDIA, which most of our customers use, and you train a model. Your model is in 32-bit floating point, and it's in TensorFlow, it's in PyTorch or it's Onyx. So any file format that is compatible with our 8-bit integer hardware. Now part of the software is the quantizer, which offers multiple techniques to get from floating point to integer while maintaining the accuracy. And in addition, there are analytics tool that gives insights to how the model will operate on the hardware, and finally the runtime that allows the host processor to whether it will be x86 or ARM based to communicate with the RunAI family of hardware such as 4-chip, 2 petaops, Tsunami 800. Now so this is the big overview. And you see the picture of untethered AI, those are Tsunami 800 cards. So each has like 4 RunAI 200s. You can go into the tool flow on the next slide. So this is the entire SDK tool flow, and as I mentioned in the beginning, we have TSN 200 running on CMC servers. So you can run some of your models there. What you will need is that you will need a pre-trained model. So we are an inference-only architecture. You do your training on cloud, use GPUs, whatever, and then you end up with a floating point model. We take that model and we ingest it. And when we ingest it, we do quantization. And the quantization, we have some special techniques where we do quantization where there's like minimum accuracy loss. There's something called like post-training quantization and quantization aware retraining. The result of this process is the quantized dual network protobuf file, which is now ready for compilation. Via compilation followed by physical allocation, the protobuf file, which contains the quantized model, undergoes a set of processing. And that processing results in an ELF file, which can be loaded into untethered AI hardware. Final step is the runtime, which runs on x86, which is Intel-based or ARM-based host, and it just executes the L1 on untethered AI hardware, returning the inference results to the host. There's this analysis box also, which is all about can I analyze this network before running it. So you can see some of the analytics software that we provide to better understand device utilization, like how much energy it's consuming, how much bandwidth data transfer is happening. And we also provide cycle accurate simulation tools also. If you go to the next one, we have some more details on each of these boxes. So quantization, this is how quantization looks like. You start with a train graph. We have tools like automated quantization, AdaQuant, and quantization aware retraining. So what it means is that quantization aware retraining is that you start from float model, you convert into INT8, and you lost some accuracy. We have a software tool flow which allows you to regain a lot of that accuracy back. And then generates PB file, which is the PB file, protobuf file, and then you convert it into L file. There's a code snippet in the bottom. It's a quantization example for you to look at. Next slide. We also have a lot of compiler optimization options. So one option is like go for the efficiency, like minimum power. What you'll do is that you'll fit in the smallest area. So you'll find minimum banks, and then you try to fit the neural network in that. Or you can optimize your performance. So you try to use as much banks as possible, multiply instances, gain performance, run multiple copies of subgroups of the network, and so on. And it's very unique for spatial architectures. So if your device or if your chip has a lot of space left, or if your neural network is smaller, you can run multiple copies of it in parallel. Next slide will, I think, show more of it. Yeah, so pipelining part of it is, so basically you can have sequential optimization of layers running on banks. You can replicate full network, both running in parallel. You can resolve bottlenecks in single layers through replication, so you can resolve part of, then you can also do some multi-layer subgraphs too. Next slide. So this is a performance comparison between CPU GPU, which is based on our von Neumann architecture and our untethered AI. So how CPU GPUs work is that you need to swap layers and coefficients from memory. So you take the input data, you go through a layer, then you bring back that layers and coefficients and batch data. what is advantageous for GPU is that you can batch data. So you can, instead of sending one image, you are sending a batch of 500 images. And that will help with throughput a lot. So, but the problem is that you lose a lot of latencies. So here's an example of a GPU running Resonant 50 in the bottom. You can see that as the batch size is increasing, the frames per second, the throughput is increasing. So it goes from 9,000, 30,000. But at the same time, the latency has increased a lot, which has gone from 0.7 millisecond to 30 milliseconds. How is untethered AI different is that we don't do any swappings. We put the entire network on the chip. We use a batch size of 1. You don't have an option to change your batch size. Although in some cases you can run like multiple parts of the network or multiple instances of the network in parallel. So you can say that those are like multi-batch. But at one time you are just going through one graph and one batch size, and you're providing low latency and high throughput. So on Resonant 50 we can go up to 80,000 FPS. It's on TSN 800, which is the 4-chip card. So it's a 4-chip number, not 1-chip number. 80,000 frames per second and 0.18 millisecond. Next slide. This is, so I was talking about like this cycle accurate simulation and simulation tools and visualization tools. So this is an example. So what we are showing you on the left is Resonant 50, how it looks like on when it's put on our Run AI device. So the darker blue are the earlier parts of the network, the heads of the network, and the lighter greens are the tail of the network. And the simulation on the right, you can see when, so this simulation chart can be generated for each of the memory banks. It will give you status on when the bank is waiting for data, when the processing is happening, when it's blocked and starved for data and so on. Next slide. This is the runtime. It's high level API. So I talked about like Tsunami 800, so that's like 4 Run AI 200 on the right side, connected to the PCI Gen 4 runtime. You can also have low level API access. So runtime library will come with Python version as well as C++ version. So you can, and you'll have access to the source code. So you can go and fix it if you want to change your parts of it, or if you want to do multi-threading and so on. We also provide you health monitoring and system management debugging tools. So like what's the temperature of the card, what's the bandwidth, and so on. So it's like NVIDIA SMIs. You can do and get all the data for GPUs. The same you can do with untethered SMI. Next slide. And next step is basically we have a bunch of demos which you can go online and look it up. There's a code sample. So what we are doing is that we are going to untether SMI and set profiling as sport. So as I talked about, there are 2 profiles, eco and sport. Eco is for maximum energy efficiency, sport is maximum performance. You download the Coco demo data and you add it to your ELF file. ELF file is basically a converted file from float 32 to INT8, and then you give part to Coco dataset. So it's very Pythonic YOLO Excel inference demo, which you can get access from our website. Next slide. So that will be all. If you want to know more about our current products and future products, so we also have a Speed AI 240 device which is coming up, and that will be available in later part of the year. You can go on to www.untethered.ai and learn more about what we are doing right now.
Thank you, Gaurav, for presentation. Time for questions. Due to time limitation, we'll maybe take 1 question or 2. Once again, if you want to ask questions, you can unmute your mic and go ahead. Yvon?
Can you clarify the status of this hardware? And actually, maybe I missed the detail. Where are you from exactly? And is this, can I buy one tomorrow if I find it nice for my project?
Yeah, you can. So what you need to do is that, so you can reach out to us. You can go to untethered.ai and there's a contact us button. And you can enter your details. It goes directly to me and I'll reply to your request. Yes, you can buy it. It's available right now. It's engineering samples we are giving right now, but we also have production version coming up in a month. But we have samples ready to test right now, and Yasin has seen it, and he has access to it.
So Yvon, we have validated the server with the Tsunami card that Gaurav has presented, and it will be available for access in the upcoming 2 to 3 weeks through CMC. So you can go on.
One or several cards?
It's one card now, and we will scale up if we have interest in it. So this is a collaboration with Entether, which has just started.
Thank you. That's a very interesting chip.
And yeah, and it's offer an advantage in the inference space to have a lot of GPUs that people use to train their model. But when it comes to inference, this was a gap that we are filling from CMC perspective, and Entether is offering a leading edge accelerator for that. Maybe one quick question to Gaurav. Yeah. Can you clarify the roadmap of Entether? So this chip is meant to be deployed in data center. Do you have plan for edge, very low power devices such as autonomous cars or? Okay, so that's good. Good to know.
Just quickly, so next device, so this one is called Run AI. Next one is called Speed AI. Speed AI is 240 megabyte and it's internally called B4. But we have like B1, B2s, and B3s. So B1 would be like 25% of B4. So it's a smaller chip designed only for auto industries and self-driving cars and so on.
Would you comment on what do you offer? What's the support to train models for that animal?
Yeah. So if you go on our website, we have a model garden which has a pre-trained set of models converted into INT8 right now. You can also go through our support portal. There's data set on like how do you convert your models from NVIDIA to Entether AI. Right now, we are giving access to our support portal through our customers only directly, and CMC will have access to it.
Thank you.
Thank you, Gaurav, and thank you, Griffin, for accepting the invitation. Griffin is a senior data scientist for NVIDIA, and in his current role, he assists customers in designing and deploying their specific compute infrastructure. And prior to NVIDIA, Griffin was a deep learning researcher for the University of Guelph as well as Google, and he holds a Bachelor and Master of Engineering degree from the University of Guelph, where his research focused on the efficiency of deep learning at both the hardware and the software level. Griffin.
Thank you so much for the introduction, and hopefully everyone can see my slides okay. So
yes,
so I wanted to talk a little bit today about the relationship between NVIDIA GPUs and all of this buzz that's happening with large language models and transformer-based models. We seem to be finding ourselves in a bit of a gold rush where a lot of what I've seen in my job is that a lot of large enterprises, a lot of startups are trying to capture and monetize some investment in the natural language processing space, and there's been a huge demand for our latest GPU microarchitecture Hopper and specifically H100 GPUs, and there's a pretty strong relationship between these GPUs and transformers, and so in this presentation I wanted to talk a little bit about what that is and why it's so meaningful. And to talk about accelerating transformers with GPUs and specifically doing so in 8-bit floating point precision, we really need to talk about something called tensor cores. And tensor cores are a name for the specialized hardware execution units that exist on GPUs. They've existed since the Volta GPU microarchitecture that was, I think, announced in 2014 and released in 2017. And these are special, almost you can think of them as like mini ASICs for executing specifically matrix multiplications in lower precision formats. And these are incredibly valuable if you're doing deep learning, because a lot of deep learning models, especially common models today, distill into, computationally speaking at least, into matrix multiplications. And so if you can accelerate that compute in lower precision, then you can really go a lot faster. And empirically, what we found, and what will be the point of this talk today, is to is to show and observe that you actually don't always need all of that precision that you maybe traditionally think you do need to make these models converge properly. And so if you look closer at what has happened since we released Volta and then a series of GPU microarchitectures since Volta, you'll notice that while we traditionally always supported a number of different precisions in CUDA cores, so just general GPU computing cores, since Volta, we now have the ability to support lower precision formats on these tensor cores. So we now have tensor core instructions that in Volta supported FP16, and then since then we've added more support for different formats. So in Turing we added a bunch of integer formats. In Ampere we supported things like bfloat 16 that I'll talk a little bit about, and something called TF32. And it was really in the introduction of Hopper that we started supporting FP8, and this is really the core spirit of what I wanted to talk about today. And so if we look a little bit closer inside the FP8 tensor cores, what you'll notice is that we support actually a couple different flavors of FP8. We support versions of FP8 with different amounts of precision and range. So we trade off a bit between the exponent and the mantissa essentially, and we find that to be critically important for maintaining good accuracy and convergence properties on a lot of models where you actually need to apply slightly more precision in some areas of the model, and you can get away with less precision or less range, for example, in other parts of the model. And so this is not unusual or uncommon if you followed what's been happening, for example, with in 16-bit floating point formats where we had BF16, I think it stood for brain float, that Google introduced, where you would trade off again the precision and the range, and NVIDIA's taken their own approach to this with something called TF32 that I didn't really talk about in this slide, but was another trade-off between range and precision that allowed people to train models essentially out of the box a lot easier with less than FP32 precision. And the other important thing to know about FP8 tensor cores is that it's not as simple as just applying FP8 everywhere. And while we do take as inputs to these tensor cores FP8 matrices and do those multiplications in FP8, we find ourselves accumulating in higher precision and then converting often as an output type to a higher precision, which is all configurable at the software level. And it's important to know that when you see us refer to this as mixed precision, that's what we're referring to, the fact that we do lower precision usually on the multiplications and higher precision on the accumulations. And this is important, again, for the reasons of making sure that these models converge properly. And so it begs the question of why would you go and use FP8 if it takes a little bit of extra massaging to make your models converge properly? Why do it at all? And the reason is pretty simple. It's fast. FP8 can help obviously accelerate math-intensive operations, and which a lot of deep learning models today are. And if you look at the datasheet for H100, you'll notice that with FP8 and tensor cores, you have 60x more theoretical throughput than using FP32 on the general CUDA cores. So obviously there's a big win to be had if you have a very math-intensive model. As well, you're using fewer bits to store your weights and parameters, and so you're going to reduce your storage requirements. And if you're doing any I/O with those parameters, like maybe passing them between GPUs, for example, it's obviously going to reduce the memory bandwidth that's required. And the last point I'll mention is that a lot of deployment of these models today happens in lower precisions. People usually quantize these networks to things like int8 or FP8 for deployment for production. And so if you're already training in FP8, essentially it's a lot easier to do this conversion. I think for anyone on this call who's done this in practice, you know that it's not as simple as just taking an FP32 model and chopping off some bits and casting it to int8 and hoping that your inference is going to work accurately. So oftentimes training in lower precision gives you some conveniences when you go to deploy this in production. And so looking a little bit closer at how this actually is able to function properly, I wanted to start describing the old way, or the old FP16 way of doing what we call this automated mixed precision. And this usually starts with taking your graph, taking your compiled graph of your model in something like TensorFlow or PyTorch or JAX, and partitioning it into safe and unsafe operations. And what I mean by this is that not all of the operations are going to be done in a lower precision like FP16 in this example. And we'll talk a little bit about more about what that means to be safe. But essentially, you need your operation to have some benefit from lower precision. So you need it to be math intensive. You need it to be a big part of your of the amount of compute that you're doing on a model, and you also need to have pretty similar dynamic ranges from input to output. So it would not be as interesting to cast something like a rectified linear unit or a nonlinear activation to lower precision format because it doesn't take that long to begin with, so you don't get a huge speed win, and because of the high dynamic range of the output, you're going to run into some numerical instability. So as well, when we do the forward pass, as I mentioned before, we're doing this in mixed precision. So the old way was to do the multiplications in FP16 and the accumulations in FP32. And then we had to do one trick back with FP16 and Volta, where in order to avoid these under and overflows, we had to essentially determine a loss scaling factor that would scale our loss and would scale the magnitudes of a lot of our like activation and weight parameter updates into the range that is representable by FP16 essentially. So in this graph, if you look at the x-axis as being some distribution of what is on the y-axis, magnitudes of parameter values, you'll notice that in the, if we consider this entire width here to be the representable range of FP32 and this narrower bar to be the range of what is representable in FP16, we would find that sometimes we would encounter situations where you're essentially clipping off a lot of the information in your weight updates, for example. And so, if we find ourselves in the situation on the left or on the right, sorry, I think my internet just cut out for a second. So if we find ourselves on the situation on the left or right, our model might not converge properly, but with something simple like scaling our loss by a multiplicative factor, we can bring our weight updates, for example, into a range that is representable by FP16 and everything works properly. For FP8, it's actually very similar. It starts in the same way. You're partitioning your graph into safe and unsafe operations. I also wanted to make the point here too that you don't always need to put unsafe operations in FP32 in single precision. You can often get away with FP16 or BF16 depending on your use case. And as well, it's important to mention that different from FP16 and FP8, we actually use during the forward pass two different types of precision formats. So we have one E4 M3 with a lower dynamic range and one E5 M2 with a higher dynamic range. And what we published in a paper here, and I have a reference to it later in the deck, is that we found empirically that in a lot of common models, I think we tested some computer vision models here, some ResNet variants, and some natural language processing models, a GPT version, and a Transformer XL. We noticed that different types of tensors in our model, for example, activations versus activation gradients, so forward pass versus backward pass, they require different amounts of dynamic range. And this is represented here by in powers of 2 for different tensors. And so while, yes, technically all of these dynamic ranges could fit into what is expressible with E4 M3, we find that to be safe, we tend to use the higher dynamic range format for backward passes where we need more dynamic range, and the format with lower dynamic range in the forward pass. And this is something that we just discovered through a lot of experimentation to work and make sure our models converge properly. And the other point that's a little bit different from FP16 that's worth mentioning is that we can't just use one single scaling factor for our entire model. There's just a lot more information loss with FP8, and to make this work properly, we actually have to use scaling factors on a per tensor basis. And the way that we do this is to watch and record a history of values on a particular tensor, like the Amax value, for example, in this recipe, to understand how to pick a proper scaling factor essentially for each tensor. So we just pick a scaling factor based on a window of past n instances of the tensor. We keep track of the Amax, and then so each tensor will have, in theory, a different scaling factor, which helps us make sure that models can converge. And so I mentioned before safe and unsafe ops. So what do we consider safe? Pretty typically speaking, things that are safe in FP8 would be convolutions, things like linear or dense layers and transformer blocks. Things like batch normalization has been tested to be safe in many cases, such as ResNet 50. As I mentioned before, things that are not safe, quote unquote, and should probably remain in higher precision are things like nonlinear activation functions and normalization. So things like your GELUs, ReLUs, softmax. Things like residual connections and LLMs and loss functions as well. We find, practically speaking, is better to just keep them in high precision. But of course, the real takeaway here is that it depends on your model, and that not every model is going to be the same. And it requires a lot of experimentation to figure out essentially what combination of ops are safe and unsafe. And so all that being said, it sounds like there's a lot of work to do to be able to apply FP8 to your model, and I agree that there is. But to make this easier, what we've done is started to develop tools such as what we call our transformer engine, which is a GitHub repository that is referenced here, which implements building blocks for allowing you to train your model in PyTorch, and with support for JAX and TensorFlow coming soon, in FP8 with a recipe that we've already developed and tested ahead of time. And so one point I wanted to make here is that while it seems like we talk about these things called transformer engines and Hopper and H100 GPUs, and they seem like they're overly specific to large language models, they're not, in theory, any more specific to one use case or another. It's just that we've prioritized LLMs and transformers because of how many people are doing that today. And so this is really the large amount of recipes that we've built for people that they can use out of the box is as it relates to transformers and LLMs. But in the future, of course, we're going to bring a lot of these recipes to other use cases, such as computer vision. And so I highly recommend anyone who has access to like an H100 GPU and wants to use FP8 to use the transformer engines if they can, to make their life a lot easier. And finally, I just wanted to share some numbers here. So we've done a lot of experimentation, and we have a paper here that I would encourage anyone to read if they're interested, talking about how to use FP8 for deep learning. And what we found is that we can make pretty much any model converge with the right recipe. We do a lot of experimenting in image classification, so we have a whole bunch of different models here that I'm sure a lot of you are familiar with. And in pretty much every case, we found a recipe that works and lets our model converge in FP8, similar to how it can converge in 16-bit floating point or in FP32. And as well as you would expect, we do a lot of experimentation as well in NLP, and pretty much by any metric that you want to measure accuracy and any model that you care about, essentially we found a way to train that model in FP8 and to a similar, if not slightly better accuracy. And then finally, in terms of performance, this was the best number I could come up with that I thought would be interesting for this talk. But essentially, when it comes to doing training on deep learning models with FP8, we find that a lot of our experiments right now we've done on LLMs, and we find that we're about 3 times faster with H100 FP8 versus the fastest possible configuration of our last generation of data center cards, A100. Where we would be training in something like FP16 or BF16. So this is a huge gain in performance in a single generation of data center card. And so I think this is really the core theme of this talk, is really just to say this is why people have been really excited about H100 and using H100 GPUs to train and fine-tune and infer language models, is because out of the box, you get this really, really big speed up over the last generation because of largely in part to FP8. And so my last slide is just the conclusion. So what is needed to make sure that your models are going to remain accurate? Well, I say just use the transformer engine recipes that we've already built, which include per tensor scaling, loss scaling. They use obviously multiple types of FP8. precision to accomplish this and mixed precision as well. What do you need to get the most performance? You need an H100 GPU, and you're going to use those FP8 tensor cores for faster math, and you're going to use FP8 IO to reduce bandwidth pressure. And I would end by saying that you should consider using this if you are training any large deep learning models, example LLMs, and you want bigger speedups on H100. And as well, if you're already using lower precision formats such as FP16 on Ampere today, this is a pretty sensible progression in your deep learning experience. And so that would be another good group of people that I think would benefit from this work. And that is it. So thank you so much for letting me speak today, and I will pass it back to Yassine.
Thank you, Griffin. Great presentation. I'm happy to see NVIDIA always making improvement in the way we use NVIDIA hardware, especially speeding up training process. So the result you have described, the speed up, can you elaborate on the speed up? You made a comparison between old GPU and new GPUs, and you said that using FP8 for older GPU can outperform the full version of the new GPUs. Can you go to that slide again, or just describe the level of speed up that you obtained?
Yeah. I'll just talk through it. I'm happy to bring the slide up again if needed. But yeah, the experiments we ran were comparing our newer GPU with FP8 versus an older GPU, A100. I say old, but it's still pretty modern, yeah, with FP16, and that was about a 3x improvement. So if you compare to a more baseline approach, which is like most people do FP32 on something like A100, then the speed up is closer to like 5x or 6x. But that was to show basically that over the fastest possible speed at which you can train a model on the previous generation hardware, we're still about 3x better on H100, which for a single generation, in my experience, is a pretty big step up. Usually you don't get quite a big leap in a single generation.
So Davis is a Canadian tech entrepreneur based in Montreal, Canada. He has been recognized as a C2 emerging entrepreneur by the Brownfield Foundation and is in the Toronto and Montreal chairperson for TinyML Foundation. He will be presenting today a leading edge tool from DeepLight running 2 Bitcoin-based CNNs on ARM CPUs. Please share your desktop and you may start. Thank you.
Perfect. Can you see my screen, Yassine?
Yes.
Excellent. So thank you, everyone. Fantastic presentations, and thank you for the invite. We've been part of CMC for some time now, so it's always fantastic to see the quality of material. Changing gears a little bit from the hardware world, and of course the two are intertwined. We're going to look at a pure software innovation that's come out of our research collaborations and internal team at DeepLight around really the ultra low bit precision trend that's been very popular, but really looking at both from a theoretical and practical side of how can we create, quantize accurate low bit models and then run them on commodity hardware such as ARM CPUs. So I'll take you through kind of the beginning and end of our journey with this approach to technology, and hopefully it'll be interesting and engaging for everyone. And quickly on my background, as Yassine mentioned, I'm one of the co-founders of DeepLight. DeepLight was founded in 2018 in Montreal. We now have offices in Toronto and employees in several countries, and are very excited to be here today. So yeah, the general trend, AI, optimize AI for the edge. The challenges, I won't harp on this too much, but of course, really, of these three, I'd say this talk really narrows in on the memory footprint challenge. When we talk about the sensor edge, the device edge, we're really limited by how much on-chip memory do we have, and the limitations, or rather the challenges of when we have to access or transfer data off-chip, because that can hinder many real-world use cases in ways that make them impractical. A lot of marginal gains can be significant at the scale of perhaps a data center or an HPC systems, but where we see a lot of value at DeepLight and with our customers is go or no-go scenarios. Either it's too big and thus too slow or too expensive and therefore impractical. And as Yassine mentioned, I particularly am involved in the ecosystem around TinyML, which used to be, categorized as ultra low power, sub-milliwatt devices. It's kind of expanded since its inception, but I'd say for context, this type of approach really lends itself most to that class of devices. So a bit more technically, what we're really talking about is in-memory or near-memory. There are various approaches here and new hardware types that's quite exciting. From our software perspective, we looked at, okay, how can we bring computation to the very edge to help augment or reduce the performance losses when we have to face this memory bottleneck? And that's why I mentioned memory, because size is the biggest challenge in this environment. Not just the size of a model in terms of parameters, but size in terms of the entire memory footprint when you load an input and want to run a forward pass on device. So more in a physical sense of course, many of us are familiar with this, type of schematic. That's what we're talking about in this specific approach with ultra low bit precision. Being a startup, of course, we interact with researchers as well as practitioners. I'd say the industrial edge AI challenges can be summarized into a handful of points. Big models and data sets means expensive training. Of course, that's an edge. It's an advantage to have large data sets that can yield higher accuracy with more complex models. The complexity comes from the data set, not the model. I think that's an important point. Industry and in different verticals and use cases can be very sensitive to accuracy drop depending on the use case. You can imagine intuitively that in critical scenarios such as, of course, when the human lives are involved, are zero tolerance versus maybe consumer, less heavy applications might have some tolerance, and that really affects how we can optimize here. And that goes not just for the optimization step like quantization, but really the entire pipeline. How the data is collected and curated, how the training scheme is approached, how much retraining is involved. That all can be factored into optimization in a sense. Third point is expecting, I would actually flip that word to requiring real-time execution. I think a lot of practitioners or adopters expect GPU level performance on all types of hardware, but the reality is that not all types of compute can deliver what the throughput that a GPU can, and so we have to try to find ways to, of course, squeeze as much performance while respecting the reality that some use cases have very tight requirements, some don't. And I think all this is to say is, life is about trade-offs. Within these challenges and with the technologies we have available to us, the most practical or efficient solution often balances these trade-offs. There's no free lunch, but the upside of that is we can often find the right lunch through generic or sometimes automated approaches. Somewhat can get us there, but often what we're finding is that more and more as deep learning is adopted in more specialized use cases, we need tailored, curated approaches depending on these challenges here. So getting more specific to deep light, and this is not meant to be a product discussion, but to give you some context of where we are active and where we're really going to hone in this specific discussion. Over the years, we've talked about our work with Neutrino, which is more model optimization, types of NAS-based optimization, and our zoo. That actually Neutrino has been available to CMC researchers for some time now. We look at this as an end-to-end iterative pipeline. All of these 1, 2, 3, 4 steps here have meat on the bone and value to add. Specific to today's discussion, an innovation that our team's been quite excited about, we're going to dive in on quantization, which is a big topic in itself, very popular, but specifically ultra low bit, so sub 4-bit weights and activations quantization for inference on commodity hardwares, specifically ARM CPUs, so the Cortex-A series is what we're talking about here. So what we're doing is coupling the innovation from the quantization side with the ability of our runtime and compiler approach, and I can talk about the tool chain there as well, to make this possible, to bring computer vision, more sophisticated deep learning models to this class of hardware, but also to really, and hopefully the results speak to that, deliver quite staggering performance improvement on humble compute. And many players in the game are recently embracing this type of compute. Sony just is one to name drop that has really ramped up its attention and investment in things like Raspberry Pis. So big picture, reduced down to quantization plus this low bit mixed precision runtime for Cortex-A. I won't get into all the approaches here. Over the years, we've evolved to test and then ultimately implement a number of approaches that we find quite powerful. That is all geared around, more for less, more improvement, more FPS, more predictions for less dollars, for less watts. Different approaches, depending on different accuracy tolerance, has, of course, different benefits. But, of course, you can see this quantization row here, leveraging, the training framework PyTorch for convolution models such as detection, segmentation, classification. On paper, you can get significant compression and maybe run it on a FPGA, for example, or a different accelerator. But we took a different approach and said, okay, let's still try to get this memory size reduction from the quantization while maintaining accuracy and deploy this on a non-specialized hardware like a CPU, and then MCU is actually the future as well. I have a couple examples there. So again, this is what we look at a holistic sense, but in this talk, I'll give results on quantization specifically. So our contribution in this arena has evolved over the years, but namely for today, QAT, so quantization aware training, that's really an important way that we leverage the data to recoup accuracy. And there's a few intricacies here I'll discuss about how much data or how much retraining do you need, and do you keep all weights and activations at a static, low precision? Are there benefits to doing it in a mixed precision approach, and what are the trade-offs of that in terms of accuracy and then losses in potential performance? But with Neutrino, we can actually quantize to arbitrary precisions, and the mixed precision approach, as I mentioned, minimizes the accuracy drop of these quantized models. That's a given. And we've coupled this with DeepLight-RT runtime, which is for the on-device inference. It's a custom ultra-low precision convolution operators that accelerate the speed and optimize the memory throughput of these quantized layers. So really, it's an end-to-end framework to deploy and execute these mixed precision ultra-low-bit quantized models on, for today, ARMv7 and ARMv8 Cortex-A processors. And I'll give some specific examples of those in a moment here. And for tooling, if you're curious about this, how this is available, it's either as a pip package or Docker image that includes all the necessary libraries and requirements. So a lot of us might be familiar with this, but there are some issues with low-bit quantization. High accuracy loss is observed when you kind of naively do 2-bit quantization, or even lower, of course. Mixed precision, so different layers and different layers within the organization of the network have different sensitivities in terms of maximizing accuracy. And so performing some kind of sensitivity analysis, there are heuristics that, of course, have been publicized and observed by many, but doing a sensitivity analysis based on your use case is important. You want to minimize the switching between different precisions. That can be a real deal breaker if it's not done elegantly. And what we've actually tried to pursue heavily is an automatic way with specifically 2-bit, 8-bit, and then FP32 layers. That's a recipe that we thought would be promising from really experiments a couple of years ago, and is what we've actually done in the last year and are improving on as we speak, with the results I'll show. But these are the issues we wanted to address, especially the last one I'd say is interesting. So in a lab environment with these academic data sets, and precision here, so this is, for 2 and 2, and then also in one example, one bit activations, but it involves the 2, 8, 32 scheme I mentioned. We're seeing quite promising accuracy retention. So, looking at classification detection tasks where we're using top 1 or MAP as our primary metrics. Of course, there are other metrics we can consider in terms of gauging how well we've quantized here. But the exciting thing is that with these paper gains in size, we have meaningful accuracy retention, meaningful enough to pursue further. And these networks are, of course, not the only networks we've tested on. It's not an exhaustive list, but I'd say it's a good sample. And the YOLO family, YOLO 5 family, has been something we've worked on extensively based on customer needs as well in recent years. So walking through what we've done with DeepLight-RT, which is kind of that other half of the tool chain I mentioned, is we found a way to have a custom low precision convolution operators that accelerate the speed and optimize the memory throughput. It's end-to-end. What I mean by end-to-end is if I'm a user of this tool chain or researcher, I can simply select my data set and model, target hardware, and rely on this stack you see on the right to deliver the best performance possible on my desired CPU. That's really the simplicity we've always gone for and achieved in this case for, the use cases I mentioned earlier. So hopefully this shows up nicely on the screen, but the way we've approached this challenge, and this is meant to be a visual representation, is taking these 32-bit and 2-bit layers that we've quantized, and then packing them in a way that can lead to these performance gains that otherwise wouldn't be possible if not packed and implemented properly, let's say. So I know that might sound a little bit vague, and partly you'll have to forgive my detailed knowledge of exactly what the team has done here, but the basic idea is having this packing approach to optimize the way we produce these multiplication outputs has really what's been not just the quantization itself, but this approach here has what's led to the throughput gains as well. So to get a little more precise, we actually use some intrinsics from the Neon instruction set for ARM v7 v8, targeting 32-bit and 64-bit ARM CPUs. This includes, single core, dual core, quad core systems as well. It's the efficient tiling and parallelization that we've used to improve upon the performance of the vectorized kernels. So not reinventing everything, you're not reinventing the wheel here, but layering in the promising nature of these low-bit layers with these schemes has really achieved that multiplier of memory and throughput savings. And on a Resin 18 model using the Cortex A53 CPU and a Raspberry Pi 3B Plus, we've actually observed 3x to 4x improvements over floating point baselines. Now, of course, that a floating point baseline I don't consider a really fair baseline, so I'll show some more kind of encouraging results. But that was our first observation. And hopefully this chart, we can share this stuff afterwards. Hopefully this chart kind of shows the dramatic nature of what's been done here. So accuracy is this line chart or line graph here where, okay, at extreme low precision, at most a couple percent lost, but the execution time is reduced by almost a factor of 10 when you talk about 1-bit, 2-bit here. And that's quite exciting. Translating that into an industrial use case, which basically means the data set's not your CFAR, not your VWW, but actually something that's been curated and annotated with the nuances of a real, real-world environment. We saw similar accuracy retention, not exactly as tight, of course, which has a few factors at play here. I'll talk about one nuance there. But what held up nicely was that coming from PyTorch framework to the CPUs, DeepLRT, above and beyond what ONNX was delivering for state-of-the-art models and the detection use case. So this is hard data that we found from our experimentation with customers. And the nuance I mentioned was that the accuracy reported on test data sets actually can be misleading. We find heavily optimized or properly optimized compressed models can sometimes have a regularization effect, meaning that on unseen data, they can perform slightly, not dramatically, but slightly better. And that's been really, really cool and promising for our customers, and something that probably merits a lot more research and investigation, but an observation to share nonetheless. This video might have a bit of lag here, so forgive me, but to try to visualize, when you're processing video, how important or meaningful this benefit is, we're seeing the stat here might be something like 3 or 4x improvement. It's a simple class problem. One class, detect person, not person, and then produce the bounding box. But this is another way of visualizing how much faster the DeepLRT low bit precision approach has been compared to something like ONNX. And this is on the Cocoa class person, not full Cocoa. So to wrap up here, this is my last slide, I believe. We actually are looking to go beyond just quantization as a standalone or a silver bullet. When we combine all these techniques, this is where I think the magic happens, and we see things like person detection running on MCUs, a large size reduction, huge speed up that actually makes, I think, in some cases, in some industries, rethink what's viable, what's cost effective for doing AI in their products. Person detection is, of course, a very popular and generic use case here, but it holds up in other examples as well. People just make for nice videos. But that's really, I think, where we're headed to continue to head here. is by combining these complementary techniques. So to conclude, 2-bit models running on commodity hardware has been presented. The mixed precision approach minimizes accuracy loss. This is a novel method. We do have a CVPR paper in Vancouver that will be presented on some of these techniques in more detail. We've benchmarked on classification detection tasks. And for future work, we do want to extend to other hardware. And I'd say the most interesting thing there is actually having native hardware support for these low-bit operations. It comes from more close partnership. That's a major area of future work. So with that, I'll wrap up and say thank you very much.
Thank you, Davis, for this nice presentation. Do you have any questions from the attendees? So DeepLight's been a long-term contributor to the ecosystem, and we have provided neutrino to our users. And also...
Can I have one question, Yassine?
Yes, sure.
I guess somehow this presentation is kind of at the other end of the spectrum with the previous one where we saw wonderful hardware where I was not too sure what tool would be used for it, and now I see a wonderful tool and I'm not too sure what specific hardware it targets. Could you elaborate on that?
Sure. So there's just two answers. By design, our model optimization is actually hardware agnostic. Some of the hardwares you've seen here, we've actually compressed and run models on because they support these frameworks, whether that's accelerator, GPU, CPU, MCU. In this specific presentation, this tool targets ARM CPUs and MCUs. So that's where specifically we're targeting with this approach here.
And do you have some path to high-performance engines, and what would they be?
Yes, high performance. Could you give an example?
Well, I mean, I could see that I could have a very low complexity, low cost, milliwatt type of device that would target an ARM. But if I want to have a high performance engine, would that be a high-end GPU, some model? Is there a spectrum of what the target hardware, top end, medium on the road, and low power?
Yeah, excellent question. I'll try to keep my answer brief. So the answer is yes, these two approaches, this model optimization, software optimization, plays nicely with these very powerful, well-designed hardwares. You may see things like 25% or 50% performance gains on such hardware versus, 5x or 6x you see on the low-end compute because by design these hardwares are already very, very optimized. So they can benefit each other. But I'd say that's one of the things we've observed in terms of magnitude of improvement. So hopefully that answers your question.
But do you actually have a specific device that you support?
Several. I can get into the typical like embedded GPU or all the way up to A100. Even some of the type of accelerators we've seen here. There's a range. Maybe one that might be interesting to you is the ARM Ethos U55 IP, which is more of a micro NPU that this approach has been tested on and published with ARM as one example.
Okay, thank you. Thank you.
Thank you very much.
Thank you, Davis. Andreas is a professor at the Department of ECE at University of Toronto, and his research interests are focused on designing performance, energy, or cost-optimized computing engines for various application domains, with an emphasis on highly specialized computing engines for deep learning. So,
thank you, Yassine, for the introduction. Let me verify that you can actually see my screen. Is that okay?
Yes.
And can you also see my cursor moving?
Yes.
All right, so let's go for it. Thank you all for attending this, and thank you, Yassine, for organizing this and for inviting me. It's great to be in a group of people that are similarly minded, and they're working towards similar goals. It's actually excellent that CMC is taking that initiative, and I think Canada has a lot of groups that have expertise that can help, and I think our efforts are fragmented. So that's an open discussion we can have later on. So my name is Andreas. I've been with U of T since 2000, and I'm going to present some of the work we've done recently in machine learning. We're lucky enough we got into this area early because I happen to be at U of T, so I saw a lot of this stuff happening quite early. This is not my work, it's work of the people that I work with. The work I'm presenting today is done by the people over here. Over the years, there's a lot more other people that have contributed to this. Some of the people have moved, actually pretty much all of them have moved to industrial positions at this point, and some of them have made significant contributions in accelerators that are actually in practical use today. Now, without further ado, I just want to say that our goal is to enable further innovation in machine learning, and what I mean by that is to develop techniques that will allow digital computing systems to punch above their weight, right? Something beyond what you're going to get by just scaling your transistors and relying on Foundry X to give you a better technology. Now, very briefly, this is stuff we all know, but let me go through that. People for decades, myself included, have been working on general purpose processors mostly. These are latency machines. They're optimized to run one or few threads very, very fast, but they're not very good for running machine learning, because machine learning at the end amounts to a lot of multiply accumulates and a lot of data transfers. I'm not trying to diminish the actual complexity of these algorithms, but at the end, the hardware level, if you go very deeply at the very lowest level, that's what it amounts to. So we've seen basically an explosion of efforts to try to build specialized chips. GPUs are very well positioned for that, but there are also many, many other startups and established companies that are trying to do something better. So the question, sorry for being a bit selfish here, is that we're an academic group, right? We get people that just finished their undergraduate degree. They're going to stay with us for 2 to 5 years tops. And the question is, what is our role, right? Is our role only to train people so they can go to industry, or can we do something more? Not trying to diminish the training, right? It's an important aspect of it. But what is the role that we can play? So I'm going to take my crystal ball and give you my view of where I think things are heading right now. There is a lot of industry efforts out there to build accelerators for machine learning. So we're going to see potentially the usual consolidation that happens. The question, though, here is the following. If you want to contribute to that, what can you do right now, right? And if you look at what usually happens with any human activity, there is in the beginning, when people start, there is very little effort that goes and you get a lot of benefit. But after a while, you get here. So you have to put a lot of effort to get something more. And what's more important here is that in order to be able to build a machine now that's going to compete, you don't have to do only something that's slightly different than anybody else. You also have to get the basics right. So in my opinion, people in academia, they're going to have a very hard time trying to compete if we're trying to recreate what industry is doing. So what we're doing as a group, we're trying to develop assists. That is, individual components that can be plugged into systems, be it at the runtime software or very low-level hardware, that will aid the current system as it stands. Our goal is to try to minimize, if possible, eliminate completely any need for change into the software. And by software, I mean the model itself, right? What the machine learning experts are doing or the application developers are doing. And at the end, deliver something that can boost their energy efficiency or their execution time performance without any effort from them. If they're willing to put any effort, we can give them a path to that. This comes from my experience with general purpose processors, where the same thing happened in the 90s, right? People were building machines out of order, branch prediction, things like that. You didn't have to design for them, rewrite your software for that. They just work for you. So what I'm going to talk about today, right, and I'm not going to cover all this stuff, is going to be fairly a lot of the effort in digital computing device design has gone into processors. However, those are latency machines that are optimized to do 1 or 2 threads very fast. They're not very good for machine learning because at the end, machine learning does a lot of multiply accumulates and a lot of data transfers. There were machines that were better optimized for that, GPUs, but people have capitalized on that, and we already saw a lot of efforts are happening here in Canada and abroad about specialized machines. It's more concrete. I'm going to tell you, I'm going to focus on the first. If there is a bit of time, I may touch upon these two a little bit too. So what is the idea here? We're also targeting machine learning training with this particular technique. Training is expensive. I mean, you had talks early this morning about how expensive it is. Let me summarize it a little bit. What happens is, in training, you do an inference pass for a lot of inputs, and then you do a backward pass. What happens during the inference pass, you're generating activations for every layer, and those you have to save, stash them in memory, so you can use them in the backward pass to update your weights. right? Even for a very simple network by today's standards like ResNet 18, we're looking at 5 gigabytes of data, right? Just for that. And of course, it's going to be an order of magnitude more for something that's really state of the art. So the question is, what can we reduce to minimize this footprint and this data transfers? Because after all, if you have to go offset, you're looking at 10 to 100 times more expensive operations than accessing things from one side. So what is the approach that people have been following so far? And there's nothing wrong. I mean, sorry, I'm presenting a little bit in a supposedly funny way, but the idea here is we're going to come up with a more efficient data type, right? We're going to guess what that efficient data type will be, and then we're going to try to make things work. And people have been very, very successful at that. So we went from FP32, which is still the default, right, to BF16 or FP16. You heard NVIDIA is implementing, and many other companies are implementing FP8. There are even proposals for FP4, right? But the idea here is you're asking the user, right, or the software API developer to come up with a recipe and a way to guess what is going to be a data type that's going to allow you convergence. What we're looking at is a complementary approach that says, you know, build whatever hardware you want, whatever data type. Can I come up with an automatic way to figure out what is a good data type to use during training? So our method is going to be a method that starts with the default, FP32 or FP16. And then during training itself, while optimizing for the original task performance goal, which is, you know, image classification or, you know, natural language processing, whatever your goal is, on top of that, it's going to learn on its own what is a good data type to use during training. And that's not going to be a static decision. This is going to change on the fly as training progresses. Now, as you know, floating point numbers have two components, exponents and mantisas. Our approach is different for the two. And take my word for it, this is the hard part, the mantissa. This is easier. I'm going to touch this exponent at the end and explain why it's easier. Let's focus on the mantissa. What happens on mantissas during training, this is an actual distribution of the mantissa values you see, right, is that almost uniformly distributed. So if you try to do some kind of form of compression, you have to be very careful because there's very little non-uniformity there. I mean, that's what compression is. What we use is a different approach. We utilize the very training process to learn simultaneously the original task goal, image classification, whatever you want it to be, plus an additional parameter. We weight this accordingly to say this is only 0.1 relevant, right? So we don't give it a very high value. But the goal of this function here is to reduce the precision of the mantissa per tensor. This alpha y is a per tensor parameter, one parameter per tensor, that says this is how many bits of mantissa you want. And these are the lambdas are weighting factors. For example, large layers should have a higher lambda. Depends on what you want to optimize. This was cross-node communication. Maybe you want the lambda to be which activations am I transferring cross nodes. These are the ones that I care about. Just to give you an idea of what is the challenge in trying to learn this is the following. We're trying to learn out of the mantissa bits how many we need to be able to converge while we're trying to converge, right? This is happening simultaneously. The benefit here is if we trim a bunch of bits, we don't have to save them to memory. So less traffic, less footprint. So we have these alpha values. In order to learn it with backpropagation, these have to be values that slowly change. So let's say at some point it's 15. Then we want at some point for the method to go take to 14.8. 14.8, what is a 0.8 bit? What does that even mean, right? So here's the ingenious part that Milos came up. This is the person that has came up with the idea. Let's say it's 14.3. How can I do that? Well, at the end, it's in retrospect, it's a very simple idea. Well, if the current precision that you have learned is 14.3, what you do is you keep the next immediate higher precision, 15, and then with appropriate probability, when you're calculating the activations in the forward pass, for some samples you use 14, and for some you use 15. So at the end you can use commodity hardware for that. But remember, our optimization here is not for the compute, even though it could be used for that if you have appropriate hardware support. It's only for the data transfer. So we are going to be storing 15 bits. 30% of the time we're going to be using 15, 70% of the time we're going to be using 14. And I hope this gives you an idea that this can gradually reduce this to 14, 12, or something less. So let's see what happens in practice. Let me skip the part about exponents. I'm going to explain that at the end. Sorry, because I'm not presenting, I have to flip through the slides that are hidden. So here's what happens in practice. What you're looking at this graph is progression in time, epochs. This is ResNet 18. We're an academic group. We have access to a few 3090s. That's how we do our research, right? And this is training with IMASNet. So 90 epochs is the default for that. And what you see along the y-axis is the number of mantissa bits. The solid lines is the average bit length of mantissa for the particular epoch. So the red is weights, the blue is activations. The bands are the spread, because remember, this is per tensor. The average could be 3.2. Some layers may require 8. I don't know. That's what the spread is. So let's see what's going on, some observations at hand. Very quickly, we drop down to some pretty stable precisions over here. This is about epoch 3. We have pretty much figured out there are some fluctuations happening which are important, but they're not changing much. So the method converges very quickly to good precisions. Next thing, it seems to be that most activations and weights on average require anywhere between 1 or 2 bits. Very, very short precisions, which kind of correlates well with the recent efforts in industry for going for small floating point formats. At the end, you see this bump because at the end we fix to specific integer precisions, right? So we can do inference with them if we want to. Let's see some other graph now. This was progression in time on averages. Let's see what happens per layer now, right? Is it important to have one precision across the network, or do we need to have various precisions across the network? What am I asking the user to really guess, right? Do I have to change my recipe? Do I have to guess all these things? What am I looking at? X-axis are various layers. ResNet 18 is not a pipeline, it's a graph. So, but first, it doesn't matter, but these are different layers. And Y-axis are mantissa bits. How many mantissa bits? The intensity is how often a particular bit length is used. So notice there are some very pale colors at the back. This is the beginning, right? We start with some very high values and slowly we drop down to, some observations. This is commonly observed in machine learning. The first and the last layer, this is a vision task, they require more precision. Not a lot, but more. Some internal layers may require more. Some layers may require even just the implied one, right? Just no mantissa bits. It's really a logarithmic-based system. The important thing is that this algorithm learns this on its own. You don't have to guess that. Now, we use this method to accelerate training when we have modeled what is the effect on a particular hardware model. We pride ourselves in not overinflating our results. So what happens here, I will explain, but I'll give you the takeaway from here. We converted training for ResNet 18 into a compute-bound problem as opposed to a memory-bound problem. On the left, the blue bar is performance, execution time. Speed up versus FP32, but for FP16 is very similar because remember this was a memory bound problem. And the red is energy efficiency. This is with our super optimistic hardware, right? So I believe on a real hardware the benefits will be even higher because memory is going to be much more expensive in practice. Now this particular method includes internally technique for reducing, sorry, I'm going to flip the slides quickly to find it, to also reduce the footprint of exponents. For exponents, we use lossless compression. The exponents have a distribution very similar to what Warren said, which is almost like a Gaussian centered around 0. Most of them are small magnitude, so we have a very nice technique we developed back in 2013 or 14 that it can encode this with only as many bits as necessary per value. I'll be happy to give you the details if you're interested. So long story short, our method can take training and on the fly trim the precisions and allow you to take advantage of whatever your hardware provides. We evaluated this with the hardware assist that I can trim the bits on the fly when you're storing and reading them back from memory. I believe that this technique can also be used as an assist for people to say, let's say company X came up with a hardware that can support FP8, FP4, FP16, whatever, and I want to train my network. What precision should I use per tensor? This tool can help you guess that. As opposed to completely guess it, you can probably use this tool to tell you, okay, maybe you should try this profile of precision. This tensors can be this, tensors can be that. And I'll be happy to talk to anybody that is interested in how we can make this a reality. Yasin, how much time do I have left? And I mean in this presentation?
You have an additional 5 minutes.
5 minutes, okay. Thank you for that. So, so let me stop here with this, and tell you about two other things we've done recently, right? We have been very lucky with our earlier work, right? It's actually in commercial products at the moment, but this is the most recent work that we're seeking to see how we can actually bring it to actual devices, right? So this is about now quantization for language models. We work with BERT or that family because we're an academic group, but I believe this technique has legs and can potentially be applied to other things bigger than BERT. So what is the idea here? This is work that has been around for 2 years now. When you're looking at the original BERT, it is weights that matter. But as you keep trying to make a transformer model look at a larger input sequence, activations become important. So we have a completely different distribution at this point, right? Whereas before was weights the thing, and activation were 5%. If we go to a much bigger activation input, the activations become the question. So what can we do to reduce that? So we have a technique that does the following. It takes a pre-trained, a foundational model, and during the fine-tuning phase, it quantizes this rapidly into very small dictionaries, so into centroids. What's important about them? I mean, many people have done quantization into dictionaries. The dictionaries are tiny, so we're looking at 8 or 16 values, tops. There are 2 dictionaries per value, per tensor, sorry, and all of them are linearly derived from a golden dictionary. So this is very rapid quantization. The other important thing is that the actual centroids, the values we quantize to, they're not arbitrarily chosen. They all fall into an exponential, and this is the second important thing. At the end, we end up with a dictionary that you do not have to implement. You can do pretty much all the calculations based solely on the indexes, on 3-bit or 4-bit values. Right? I'll be happy to tell you the actual details if it matters, but at the high level, this is the marketing slide, if you wish. This is a 4-bit quantization for both weights and activations. It's post-training. It does not require access to a training data set, only the target set you want to do. It does not require you to do multiply accumulate if you don't want to. You can just count indexes. That's it. And at the end, even if you wanted to do multiply accumulate, you can do fixed point compute, because the dictionary itself is fixed point values, even though you don't have to translate to that. And the final thing I wanted to talk about, sorry, give me a second, is the technique for reducing the volume of fixed point values that you use during inference. And the goal here is the following. When you have a typical system, sometimes you have to go off-chip, and this communication is very expensive. Right? The energy can be 100 times, the latency can be 50 times versus an on-chip memory. If you have a large chip, maybe you don't have to do that, but you have, if you have a very large network, you may have to do that. And even in some cases, you have to do this cross nodes, which is even worse than going to a local DRAM. So what people do today is they try to quantize to a particular data type, 8 bits, 4 bits. 8 bits is standard for vision tasks, 4 bits, 3 bits, or whatever you want. But at the end, as Warren also mentioned, at the end, the distribution looks like this. Most of the values tend to be very close to 0. And depending on how you train your network, you may have a few outliers, but there's very little over here. When you pick a data type, you're picking a data type that can support all of those magnitudes. And at the end, most of the time, you're storing 0 bits. Question is, what can you do? There is a method, some of you may know it, it's called arithmetic coding. I'm grateful to my students that introduced me to that. I failed to learn this as an undergrad. It's a method that takes any arbitrary input sequence, right, of symbols, in this case it's going to be fixed point numbers, and converts it into a single real number. Right? Think of it, it's not exactly a floating point number, it's a fixed point number, but it's a real number. The gist of the method is that the real number uniquely identifies the sequence. Right? So you can take that single number and convert it back to the sequence if you want. The next important thing, and this is the downside, is the number of digits this number has depends on the sequence itself. So it's not like 1 or 2 bits, it can be thousands of bits. But if some values here, for example, zeros or ones are very frequent, you may end up using less than a bit over here. So this is the power of this method. It's called arithmetic coding. It's been used extensively in scenarios where compression, like off-chip accesses or any kind of communication, is very expensive. And the method itself is very expensive. We have a very practical implementation that is a variation of it that works for machine learning and can cut down traffic to about half for most networks we tried so far. So I'm going to stop here and open for questions. Thank you for inviting me.
Thank you, Andreas. We'll take some questions from the floor. If you have questions, you can unmute your mic and ask Andreas. Andreas, this is a great presentation, and it's really helpful for people who would like to explore the quantization and optimization of deep learning models. And I think this is a must-needed feature going forward if you want to be able to deploy AI at the edge, especially, and bringing this. There's a lot of collaboration opportunities among the ecosystem. I see presentation from other speakers who are working on similar problems, and I think this is a very good opportunity. So professors and students reach out to you for collaboration opportunities. So is this the main channel, just to reach out to you, or you have some GitHub repository where people can replicate the same results and then maybe use some of your work?
I'll be happy to talk to anyone. First of all, I'd like to thank you and CMC for taking a leadership role at this. I think it's sorely needed in Canada, right? Other countries are doing better, as always, right? And I think there is a lot of talent, a lot of very talented people, both academic groups and students that are coming out, and I think we're failing to capitalize on that. The emphasis so far in Canada has been on the software side, which at the end is the most important thing, but I think there is an opportunity here, right? Anybody that has an interest in that, I'll be happy to talk to them. And one final thing I will set up, it's extremely difficult to maintain and build expertise as an academic group. I'm sure it's hard in industry too, because we work with people that stay with us for 2 to 5 years, right? And we need kind of, as long as these things are interesting to people, we need some kind of support, right? And I think we have a good basis here to go to the government, because at the end it has to be them, right? You cannot ask a startup or a small company to do this, to provide some continuity here, right? And I'll be happy to talk to anyone that's interested in doing that.
And I absolutely agree with you. HQP is a critical piece of this.
Hi, Yassine.
Hello, everyone.
Can you hear me?
Welcome back. Yes. Hello, everyone. Welcome back to this workshop. We will resume with our next presentation from Professor Warren Goss. So, Warren, will you share your desktop?
Thank you. Do you see my desktop shared?
It's coming up. So Warren is a professor and chair of the Department of ECE at McGill University in Montreal, and his research focuses on signal processing, system design, and custom computer architecture. And today's presentation from Warren will cover standard deviation-based quantization for a deep neural network. So you're Warren.
Thank you very much, Yassine, for the kind introduction. Just wanted to verify that you can see my title slide and hear me okay?
Yes.
Okay, great. Wonderful. Okay, so I'll be presenting the work of my group today on mapping efficient neural network models to low complexity edge devices, and the particular topic of today's talk will be on quantization for deep neural networks. So the topic of this workshop is around edge intelligence, and there are a number of benefits to doing machine learning on the edge devices, on low complexity devices. The first is that it addresses the issue of security, cybersecurity, so your private data doesn't have to be sent to the cloud. As well, for applications such as autonomous vehicles, there is a quick, low latency ability to adapt to the environment. And so this, by avoiding the communication with the cloud, this means that latency can be reduced and power, the significant power that would require to do the wireless communications to the cloud can also be addressed. So with that in mind, the goal of our work is to take the tasks involved in machine learning, which are training and inference, training normally being done in the cloud on servers, and the inference being done either in the cloud or on edge devices, and putting these onto a single low complexity edge device. So migrating the high precision task to a low precision implementation in hardware. And the different approaches that we've been taking to that, one of them is pruning and quantization, so even down to sort of extreme quantization such as binary or ternary 1-bit or 2-bit quantization levels, but also other techniques such as model compression with distillation, neural architecture search, heterogeneous architectures using CPUs and GPUs, as well as on-device learning. And we've actually been focusing that work on language models such as BERT, where we've been looking at fine-tuning pre-trained models to adapt to specific language tasks. And we're doing this on edge devices. And then finally, we've also been looking at new hardware architectures, for example, stochastic computing, to solve this edge challenge. So in today's talk, I'm going to focus on the first of these, which is quantization of deep neural networks. Okay, so here is one layer of a deep neural network, and it shows the data flow through the matrix multiplication, such as convolutions, then some normalization, for example, batch norm, into a nonlinear activation layer, for example, ReLU function, and so on. And then the inputs are activations, X, and weights, W. And actually, we saw this in earlier talks today, that when you quantize, it actually makes sense to focus on the heavy computations, right? So you see here that the heavy computations are the matrix multiplication, the convolutions. This is where you can get the most savings by quantizing, and also it's safest to do it. And then the rest of the computations on the right here, this is very cheap. So we don't focus on quantizing this, but instead we quantize this. So we're going to quantize the activations and the weights so that they can use in the matrix multiplication. And we can do integer multiplication in the convolution unit instead of floating point computation, and use fewer bits. So how do we do that? This is a layer by layer approach, and let me explain it with an example. What we're going to do is we're actually going to assign the same number of bits for every layer, but we're going to use different scaling values. We talked about scaling values. I think Griffin talked about these scaling values before. I'll give you an example of what that means through this example. So let's say we have a value 0.3649. This is some high precision value represented in, say, 16 or 32 bits. And then we're going to want to quantize that for the heavy computations. So we're going to bring that down to an 8 or 4-bit value. And let's say for 4 bits, we represent it as the number 5, binary 0101. Okay, so now we do the multiplication with this integer value 5, but it actually represents a different value. It represents the value scaled by a factor of 0.066, which when you scale, that ends up being 0.335. So you can see it is quantized. There is some approximation error. But what you see the process is you quantize to a low number of bits, and then you scale up to a high precision value, again with a scaling factor. And what's going to be changed layer by layer is the scaling factor. So this is a method we're going to present, which is how do you learn these different scaling factors that you should use in different layers to give unique quantization for every layer. And there are two main approaches to quantization. So let's say you want to quantize weights, and what we find is that weights typically fall into some distribution that is not uniform. Typically, it's bell curved. It's Gaussian-like in appearance. And so really what the idea here is to try to fit a quantization scheme to the distribution of the input, the activations, and the weights. So to try to find one that looks like a bell curve. Now, there are two ways to do this. The first is to treat this as an optimization problem and to minimize the error in the quantized scheme and the actual data you're trying to fit. Okay, so define the best quantization steps, sorry about that, that fits the distribution well to minimize the error in representation with respect to some number of bits that you've chosen. The other way of approaching this is to treat it as a machine learning problem, and it's to learn a quantization scheme, which might look very different. Here's one that looks very different. And the objective here is not necessarily to minimize the error between the data and the quantization scheme, but to find the quantization steps that produce the best overall task accuracy. So to see what scheme actually gives you the best performance on your machine learning task. And we're going to take the second approach with our quantization technique. So just a brief introduction to quantization. Here's a quantizer. This is a simple linear quantizer with uniform quantization intervals. And so the quantization interval is this step here. Here is all just integers, steps of 1. Okay, and so very easy uniform quantization pattern. But what we do find is what we're quantizing is not usually uniform. It's usually, like I mentioned, Gaussian-like in its appearance. And this comes from different ways we train neural networks using gradient descent with L2 norms or batch normalization. This tends to produce weights or activations that have these bell-shaped distributions. And so the implications of that are a huge proportion of your weights and activation values are actually close to 0. There are relatively few far away from the mean, which is 0. So the idea being we should be focusing our efforts on precisely quantizing these weights near 0 and not really worry so much about the ones out in the tails. So here is an example of how we can do that. There's two ways. There's a linear quantizer, which I showed you before, and then there's this non-uniform, we call it a power of 2 quantizer. And so the uniform quantizer is shown in red, and you can see that the steps, the red lines here, are all equal size. And you can see this is a 3-bit or a 8-level quantizer with the value 0, 1, 2, 3, 4, 5, 6, or 7 is what we quantize into. Contrasting with that, we have the non-uniform or power of 2 quantization, where the steps, again, there's 8 of them, but they're not uniformly spaced. The step sizes get larger and larger. In fact, each step size is a factor of 2 larger than the previous one. And what we see is by doing that, more of the information is retained in this region here, closer to 0, because of the the non-uniform distribution of our data. It might make sense to use this non-uniform quantizer. So the scale is the height of this first step, and you see for the linear one, it's 1. But you'll notice that even though the integer, the quantized value that you're going to work with is 1, it actually represents a value, let's say approximately 0.6. So that's why you need to get this scaling factor to scale after the quantizing is done. Zooming in, for the non-uniform quantizer, the scale is the size of the smallest interval, and there's more finely grained quantization happening close to 0 than compared to the uniform quantizer, which would have quantized all this region just to 0. Okay, so how do we use this? First of all, we in the training, we do the quantizing in the training. So we have the weights and the activations in high precision. We quantize these, and then we have the quantized input and weights, and we store the scaling factor that we determined in the quantizer. Then we do the matrix multiplication in low precision, for example, 4 bits, and then do a rescaling up to a high precision using the scaling factors. Now, in inference, we have the quantized weights stored in memory from the training, and then we take the input in, we quantize it just using a comparator with steps that we had learned in the training, do our low precision matrix multiplication, and then in the rescaling step, we use the factors that we had learned, scaling factors we had learned in training. Now, the note here is that the scaling is something we can merged into for no cost into the batch norm computation. So it's kind of for free. Okay, so the quantization we do first in the training, the first step we would do is to normalize the data, but in such a way such that the minimum value of our data will be mapped to 0 and the maximum value will be mapped to 1. So we implement that by clipping our data at some parameter alpha. So we just say that if the value is greater than alpha, we clip it to the maximum value of alpha, and then we divide by alpha, and that produces the distribution we're looking for. And there's two ways to then find this parameter alpha, this clipping threshold, either by solving the optimization problem I mentioned before, or by finding alpha through gradient descent and backpropagation to learn the value of alpha, the clipping threshold. The way this has been done in the past is a technique called PAT, parameterized clipping threshold. And you can see here's the threshold alpha. And so the idea is to learn the optimal place to do the clipping. And this is done through backpropagation. The problem that we see here is that because this is 1 alpha for the whole layer, you get the gradient by adding up all of the gradients coming to the layer together, which actually makes a very large value. And this is bad for numerical reasons. Either it grows very large or it vanishes. We saw in the batch norm paper that to ensure good convergence, what you have to make sure is that your gradients are kind of along the same order of size as your parameters. And so to do that, you have to scale alpha when you're learning it. And so our approach to the scaling is to apply a scaling factor to alpha in the learning. And we scale by the standard deviation sigma. So instead of learning alpha, we're learning alpha sigma. Now, the intuition why we do this is, first of all, this gives a meaning to alpha. Instead of just being an arbitrary value, it tells you how many standard deviations from the mean should I keep of my data and how many can I throw away. And also, provides a way for the optimizer to actually have knowledge of the distribution. And so this goes into the backpropagation, and we can learn alpha that way. Just as a note in the box here, we can generalize the gradient computation to include a couple of factors, a scaling factor S and a decay factor. So this will come up a little bit later at the talk, just very briefly, what we can do by modifying the scaling factor. Okay, so the results I can present here. First, I'll present the results on CFAR10, a relatively small data set, using linear quantization with both ResNet and small VGG architectures. As a baseline, the ResNet 20 with 32-bit floating point gets you an accuracy of 91.8%. And we can see that our technique actually, I think Davis mentioned this, because of a regularization effect, can slightly actually outperform even floating point accuracy. So that's not necessarily unexpected. And it does outperform previous techniques with 5, 4, 3, and down to 2, even 2 bits of precision for the activations and the weights. And we looked actually both at activating, in quantizing both the activations and weights, and just the activations alone, and we still see an improvement. Similar results for small VGG, where we can get the accuracy of full floating point implementations, but with only 2 bits of precision for activations, and down to even as low as 1 bit of precision for the weights. So extreme quantization. On ImageNet, again using linear quantization, it was hard to do an apple-to-apple comparison to previous work because they use slightly different versions of ResNet, and also there was some different kinds of data augmentation happening. So what we've done here is to show you is we've calculated the difference in precision and accuracy, accuracy between floating point and say 4 bits quantization or 3 bits quantization, and in fact we gain a little bit in under 4 bits precision, but we do outperform the other work, for example, we only lose 0.1%, where other works are losing on the order of about 0.6. On AlexNet, we're also achieving very good accuracy, floating point accuracy with 3 bits, and relatively close, but still, leading result with regards to 2-bit precision. Finally, just a couple quick comments. There was that scaling factor we had in the gradient computation. We can actually use that to move the clipping threshold left or right. And by doing that, we can affect how many of the values, the weights are pruned down to 0, which actually has a positive effect in terms of complexity of the network and implementation. So this is a trade-off that we can tune and trade off pruning ratio for accuracy. And finally, this last results, this is the results for this non-linear or log2 power of 2 quantization. And what this shows is that the accuracy on ImageNet is competitive, slightly better than previous work. But I think the takeaway here is we found that compared to, say, state-of-the-art technique, which is S-cubed, our method required 4 times less memory during training and also converged much faster, converged 10 times faster. So in conclusion, we've proposed a new quantization method that takes advantage of the knowledge of the distributions of weights and activations through the standard deviation. The proposed method outperforms prior art in various image classification tasks. And the non-uniform version of this converges very quickly, up to 10 times faster than state-of-the-art. And we also have a way to flexibly trade up accuracy and network size by controlling the pruning ratio. In future work, we plan to apply this method to transformers. So with that, I'll thank you very much for listening.
Thank you, Warren. Great presentation, as usual. Any questions from the attendees? If I ask one simple question about your future work, which is applying this method to transformers, do you have any models in mind, and what is your plan in terms of like using the infrastructure to do that?
Oh yeah, so we've been focusing on BERT models and various low complexity, smaller versions of BERT. So that's where we'll be focusing. Okay, so it's really toward, when you say small version, toward the edge AI more than... Oh yes, we're looking at definitely edge AI and doing this on for example, mobile GPUs. Great. Any plan on deploying this on like heterogeneous edge devices that combine, for example, different type of accelerators, such as FPGA, GPUs, and other? Yes, in fact, we've been looking at specifically the combination of mobile GPU and mobile CPU. So that work is ongoing. Our next speaker is Nizar. So Nizar is a postdoctoral fellow working on the Polara IPU. He's received his PhD in 2022, and he's currently working with a team to deliver multi-core RISC-V vector processor for AI inference on both FPGA and ASIC with the software stack necessary to run this accelerated AI workload. Nizar, the floor is yours.
Thank you. Can you hear me and see my screen?
Yes.
Hello everyone, I'm here to present the work that my group has been doing as the title calls Polara RISC-V multi-core vector processor. So first we're going to introduce what is Ariane, ARA, and Polara, why vector instructions are important for AI. Then we move like what the research objective of this project, and we talk about sub-byte computation methods, our specific Polara implementation, and the custom AI framework to run AI model on the hardware, and we finally conclude. First of all, the CVA6 or Ariane is an open source processor from developed by ETH Zurich, and we're using it in our design. It's a 6-stage in order decoding out of order execution. We support multiplication, atomics, and compression extension. It's available on the OpenOrder group repo, and we're using connected to Ariane or CVA6 a vector coprocessor called ARA, which also developed by ETH Zurich, but we're modifying it a little bit to add some bit serial operation and other operations. The ARA is compatible with the RVV1.0 vector extensions. So it's somewhat similar to an x86 AVX instruction or ARM Neon instruction, but it's a vector processor instead of an array processor, which has its own advantages. Like, for example, it can support vector lengths up to 4096-bit, as opposed to the fixed instruction satisfied at AVX, for example. And ARA can be configured with a different number of lanes to accelerate the workload, while Polara is an implementation of ARA, which uses 4 tiles. So basically you have a quad implementation of ARA, each with quad lanes, and we connect everything using OpenPython, which is with the help of University of California, Santa Barbara group. This is the design that we're planning to build. Just a quick recap of SIMD instructions. It allows us to execute data vector operations with the benefit of data level parallelisms for better hardware utilization. And so a vector and an array processor are a kind of different implementation of the same idea of a single instruction multiple data approach. So it is very widely used in AI, like vector instruction are widely used in AI. Some of the most common operations are XP and matmul, and this can be accelerated using vector instructions. Instead of using regular per element operations, you can use vector operations, which can cut the execution time of these different operations. So as for research objective, like we are extending ARA to support low precision instruction and sub-byte computation. This would help like with low precision neural network model and binary neural network models. We are building a FPGA model of the chip for verification, and we're building also like custom ASIC with that Polara implementation with the help of CMC using Global Foundry 20nm process. We're also building a software framework in order to run some of these operations on hardware. So first, like, let's quickly introduce sub-byte computation methods. So we are supporting 2 types of bit serial computation method. One is called bit serial, and the other called ULPAC. So in bit serial, you are transforming a multiplication, for example, weights times activation. Instead of doing it in a floating point unit or a regular multiplication, you can instead use a pop count instruction and a series of additions. So that way you can reduce some of the multiplication hardware on your device. Another approach is to use ULPAC, which does integer operations. It does multiplication, shift, and then accumulation repeatedly on the different hardware. But you can use sub-byte weights and activation, and that would result in a speed up and a good speed up. This is an example of what performance you can expect with bit serial and ULPAC. For example, at the bit serial with 1 bit weights and activation, it should be like the fastest compared to regular int8 operations, while ULPAC is slightly slower at 1 bit 1 activations. But as you increase the number of weights and activation, the bit serial operations start to break down a little bit, and after a while it would be less efficient at higher weights than using regular int8 operations. So for binary network, it's good to stick with bit serial, but for more slightly larger sub-byte computation, it's probably using ULPAC. So one of the benefits of ULPAC that can be done is either software or with hardware acceleration. So this is a single implementation of ARA, which has 4 different lanes, and as you can see, the lanes are the ones that can do vector operations, are what takes the most space in a single ARA node. And we have actually proposed several type of cores. The ones that we're going to have is the ARA. but we have different implementations. So some will be on FPGA, some it's just purely on simulation. As for the ARA, is the biggest one. We have a co-work which remove all the multiplication and floating point and only support bit serial operations. So this would be like good if you have bit serial operations. A Spark is a different implementation that does have integer multiplication and division, and also integrate a new instruction like a vectorized multiplication shift accumulate, and this would be good for ULPAC. So it will accelerate ULPAC a little bit. We have also Spark V2 in work, which kind of does the vectorized shift alone as a different instruction instead of mixed instructions, and it's more configurable. While it's slightly bigger in size than others, we are working on reducing the size. Currently, it's still a work in progress, but we expect to be much smaller than this one. So this is a summary of what sub-byte computation can be. So for example, if you're doing regular FP32 at the same clock speed, you can have up to 12 operations per cycle, while if you're doing bit serial using Quark or the bit serial hardware, you can have up to 51 operations per cycle. As you can see, as the weights grows, the benefits reduces for Quark, while ULPAC doesn't diminish as much, and ULPAC can be done software only, but if you have the additional vector instructions, you can have some speed up compared to not without hardware acceleration. Now, as I showed before, like this is the architecture of Pollara with the 4 different tiles, and in order to work, we had to modify ARA. An example, we had the Axie to Noka bridge. We have first test integration, mostly passing for RISC-V vector for one tile, and we are working on getting multiple tiles to work. And as for FPGA, we have, with the help of CMC, we have access to an Alveo U2080 board. We have a bit stream generation of ARA, and we are still adapting some of it to run ARA on the FPGA hardware. We will be using like the 64-bit exit signals and UART, other clock and reset, and we are expecting 75 megahertz on the FPGA emulation of ARA. As for the next step in FPGA emulation, after we finish ARA, we can try with Pollara, but with one tile to integrate, to see how it will integrate with OpenPython. And so we are using, like I said, OpenPython in order to scale from one tile to multiple tiles. And after we finish one tile with OpenPython, we can try to scale it more to 2, 3, 4. I don't think we can fit 4 in an FPGA board. We'll probably be 2 and 3. And then we can test some additional tests on Pollara. As for the ASICs that we're fabbing, planning on fab. We are planning a tape out this summer. We're using GlobalFoundries 22 nanometer. We are expecting 750 megahertz clock speed with a 3x3 millimeter die. As for this is a simple design. We have 4 tiles, each with 4 lanes. And the ARA macros are pretty much done. We are finalizing the OpenPython tile macro, and we are working also on top-level macros. This would be a single macro for and single layout for a single tile. As you can see, it's this tile would fit here. Like this is the one tile of ARA. On the other side, you'll find the PMesh stuff for interconnect and L2 cache and L0.5 cache, and the OpenPython would handle synchronization between different cores for data coherency. There is still, so this would be the layouts of the chip. We still have a file integration to do, and we are still working on some of the top-level bridges and other stuff with the help of OpenPython group from UC Santa Barbara, as we said. As for timing, we still have small violations to fix for 750 megahertz clock speed. Currently, this is but at the worst case corner. So we are expecting this to be fixed in the upcoming weeks before the deadline for submission. We already have the application ready, and we are waiting for the deadline to finish everything before. And the tape out should start then, and we expect a delivery date in the early next year. As for running some AI workload on chip, currently you can either run AI workload on like an operating system, or you can try bare metal. In our case, the CVA6 does have an MMU, so memory management unit, so you can boot Linux on the chip. However, there is a lack of MMU on the vector processor, which means running vector code in the OS is not supported currently. So we are looking to get an AI runtime to work directly on bare metal. So running on bare metal does have an advantage of reducing memory translations and memory accesses, so it will help a little bit of performance and power efficiency. However, you lose some of the benefits of having operating system to manage some of the complexity of memory allocation and memory stuff for you. So what we found is like there's a framework called Keras2C, which it has two parts. It takes an input Keras model, and it will transform it into statically allocated C code with like all the weights and bytes is statically allocated in files, and then you can and it will also generate some of the operations that you require to do training to do the inference. And there are library files written in C where you can execute some of the like the operations such as conf2d, dance, LSTM, and different activations and everything. And it's an open source framework that's already available. So basically, you take that model, you compile it into once you run that code gen, it will compile into several C code, and then you take the C code, you write a custom make file with between the generated C code and the library file to compile into a binary. Then you run that binary. We tried it on like x86 and ARM-based devices, on Windows, on Linux, and for our device we run it on Verilator, so it's a simulation of the RTL for RISC-V, and we also run it on Spike, and as you expect, everything would have the same result, exactly the same result on whatever systems that you're using. Now, we didn't stop there. We just also tried to create a fork of Keras2C for specifically for our environment. So we had different implementation of some of the standard C library calls, and also we're starting to work on int8 and FP32 or the FP32, but fixed point implementation and int8 implementation of different popular kernels like conf2d, add, dance, matmul, some of the more common layer, and we're building support like gradually for each one, both on the code generation part and the library part. But most operations are still in float, and the one you need a specific operation to work on accelerated hardware, then you can. For example, some of the performance profiling we are seeing 97% of clock cycles are being spent in conf2d when you're doing scalar operations, so it makes sense to optimize some of the more compute dense layers first before you move on the other layer. This is a very simple example of a like early result of the frameworks that we're working on. Just running the vector core, and we count the number of cycles to run the exact same network on a Raspberry Pi 4 device, or an Intel 12 Gen core, or our custom ARA core. We can see like the clock cycle required to finish the workload is significantly smaller on our hardware, while our clock speed is a bit smaller than Intel. So there is on the 12th gen core, Intel would be faster because it has significantly higher clock speed. But when it comes to the number of clock cycle required and the instructions per cycle that we can achieve, it's higher than Intel, especially like if you're starting to use optimized int8 kernels. However, when it comes to energy efficiency, we are way ahead of anything ARM or Intel are doing, at least based on the simulations and that we're having. And basically, we are still the work's still not done. We are still working on finishing some of the RTL for Spark v2. We have an FPGA implementation for Pollara also on the way. There are still some validation testing for Pollara, and we are still adding support in for the software framework to work with Pollara for future work. And we are expecting the chip, as I said, in 2024. So basically, this is it. Are there any questions?
Thank you, Nizar, for this intense presentation. There's a lot of details.
Yeah, I want to go so fast.
I am happy to see. This successful collaboration in the ecosystem involving École Polytechnique with this team of talented researchers and CMC and ETH Zurich. It's a very successful story, and I hope it will help the rest of the ecosystem reuse these cores and learn from your experience as well. Any questions from the audience to Nizar? I think since we are running out of time, we will jump to the last but not least presentation. François, can you share your laptop? So François is an assistant professor at École Polytechnique de Montréal since 2019, and his research interests span digital system design, telecommunications, and machine learning with applications in next-generation wireless communication systems, energy-efficient AI, and other low-energy digital systems. François, the floor is yours.
Okay, so thanks for the invitation. Can you hear me, see my slides?
Yes, yes.
All right. So today, I'll be talking about designing robust DNN models in particular to exploit energy reliability trade-offs. So I guess in the community that focuses on accelerating AI, we're all focused on trying ultimately to improve the energy efficiency of these models. And so I'll present essentially a complementary direction that we can pursue to continue improving this energy efficiency. Right. Okay, got it. So let's start by just putting energy consumption of current energy consumption of AI on the hardware that we have in perspective, right? So I did some little back in the envelope calculation by trying to find some source. It tends to be a bit hard to find the actual energy consumed by AI. It's something that companies are not always keen to divulge. But here I found some numbers for a large language model. And apparently, to answer one query, so run the inference specifically through that model would need about 4 watt hours. And so I imagine like having a conversation with a robot, and you would have maybe, you would say maybe 3 10-second sentences per minute. And so I come up with this figure that, our conversation robot is using about 720 watts of power in order to maintain the conversation. Right. And then we can think also of maybe self-driving, which is the other, big application where we're trying to compete with humans. And there it's even harder to find numbers. But what we can base ourselves on is this new platform by NVIDIA, which is aimed at full self-driving of cars. And it's composed of 2 GPUs and 2 SoCs on one board. And the whole thing has a 800 watt thermal envelope. Okay. And all these things can be done with our human brain that consumes about 20 watts. So we see that there's still quite a gap in terms of energy efficiency of AI. Okay. So what can we do to improve this energy efficiency? There's a lot of different directions that are being explored simultaneously, and I think they're all ultimately needed to achieve the energy efficiency of the brain, and maybe more. There's no reason we need to stop at the energy efficiency of the human brain. So the key, as was mentioned in other presentation, is it's really data movement that costs a lot. So every memory access, and in deep learning we have a lot of these because we have to retrieve all the weights in the model, and the models can have billions of weights. So that's a lot of data movement. So we want to reduce that. So we can do that by moving as much as the model as we can on chip, using specialized hardware that's going to be more energy efficient. And one of the maybe most promising, I think, development in hardware is going to be in memory computing, where we avoid having to retrieve model weights from memory because we can directly do vector matrix multiplication in memory. Okay, but so whenever we try to push the energy envelope, the efficiency envelope, we end up finding these trade-offs between energy consumption and reliability. So here is the first example with SRAM chips. Just two experimental results that I took from papers where we can, clearly see this now well-known exponential relationship between the error rate that we observe in the memory and the supply voltage that we give to that memory. And there's a quadratic relationship, as you probably know, between supply voltage and energy consumption. So reducing supply voltage is a great way to make energy gains, but at some point it comes with these reliability concerns. Okay. And the other very interesting place where we see this kind of trade-off is when we do computing in memory on a crossbar. So on memristor crossbars, we're able to present some voltages on the rows of the crossbar and sum up currents on the columns, and that allows us to do vector matrix multiplications involving, for example, DNN weights directly in memory. And with great energy efficiency. So what we end up implementing is this equation here, which is a sum of weights times some input vector with a scaling factor. Okay, and so we have the weights represented as conductance values, the input being the input voltage, which could be, in a DNN would be the activations coming from the previous model layer. And finally, we read out an output voltage, which could be converted back into digital domain to do further computations. So yeah, this approach has very high density, is non-volatile, so lots of really nice advantages, and above all, energy efficiency. Okay, but it has a number of challenges, and the main one is highlighted in red, is that there's a lot of noise that affects this computation, and because the computation takes place in analog domain, it's directly exposed to that noise. So we have both variations between different memristors and also cycle to cycle. So in time, there could be drift in the devices and so on. Okay. So one way to model the reliability of these devices is with a relatively simple additive Gaussian noise model. Again, this is a figure taken from a IBM paper about their phase change implementation. Okay, but it's the same idea with other resistive memory implementations. So we see that there's here if you can see my cursor, hopefully there's this relatively Gaussian distribution that we see of conductance values, and what they're showing here is that additionally variance, so that the parameter of the distribution can also vary depending on what the target conductance was. Okay. All right. So I've talked about these energy two interesting places where we see these as energy reliability trade-offs. So the rest of the talk I'll talk about how we can train models that are robust to that kind of noise on the weights of the DNN model, giving you so first an overview, and then I'll talk about some recent work of ours where we use sharpness aware training to improve robustness. Sorry. Yeah, so I can hear somebody is speaking in the background. I don't know if you could mute him or her. All right, moving on. Okay, so first I'll give an overview. Actually, I went back to one of our old paper on the subject that we published in ISCAS conference in 2019, so now it's almost 4 years ago. And I was pleasantly surprised that a lot of the conclusions that we had, or not the conclusions, but the directions that we identified as promising for studying model robustness are still current today. So I want to go back to this paper basically to give you an overview. So in this paper, the starting point was that we have this energy reliability trade-off when we store information in memory, so which is given by the exponential model that we saw earlier, right? So we have basically for any energy, normalized energy that we require to store a bit, we can, there's an associated bit flip probability, okay, which is exponential. And the other assumption in that paper, which is not terribly important, but is that we could detect errors that happen in the model, and when we detect them, we do two things. If there's an error on the sign bit of our weight, we detect that and we replace the weight with the 0 value. And if there's an error on any other bit, we replace that bit with the sign bit. So that means that all our deviations, our errors on the weights are going to be towards 0. Okay. But again, not terribly important, just to put in context the results that I'll show. So the first general principle, I think that we can identify is that DNN robustness here, as we can see on these figures, depends on the architecture that we choose, so the DNN architecture. So here we trained 4 different architectures on the exact same task, which is image recognition, CIFAR-10 data set. And we look at test accuracy versus either the bit flip probability or in terms of the energy that we need to consume to store the model. So in both cases, we see it varies quite a bit. This is just what I want you to notice. It varies quite a bit depending on the architecture. Okay. The other interesting aspect is that different parts of the model are going to have different sensitivities to these bit flips or to noise in general. So again, here we took a particular ResNet model, which had 4 blocks of layers, and we looked at sensitivity to bit flips in different layers, and we can see it's quite different in each of the 4 blocks. And we can kind of look at the relative sensitivity of the different blocks, and we can come up, I'll skip through that, with a rough rule here as to how we should assign the reliability to each layer. So we might think that the weights associated with one layer would be stored some would be stored in more reliable memories, and some would be stored in less reliable memories. Okay, and the results that we get are as follows. Still CIFAR-10, so we can compare. Okay, our reliable implementation uses some amount of energy to store the model and achieves some test accuracy, this is pretty much state of the art still accuracy that you get on CIFAR-10. Okay, so that's the starting point. And then we see what happens if we allow faults to occur in the memory. And we see that we find some sweet spots where if you reduce the reliability of the memory in order to save energy, you can actually do better in terms of energy at equal accuracy. Okay. And then what you could do additionally is that you start training with noise. So you take into account the memory, the bit flips that you'll experiment during inference. You take them into account during training, and prepare the model to live through that, and then you can make significant gains in accuracy that way. Okay. Then this brown curve is if you start assigning reliabilities differently for different sections of the model. And if you put all of this together, you as one might expect, you do still better. Okay. The other important aspect of these of model robustness is that it's just one of many methods to improve energy efficiency, right? It cannot be used alone. And we see, like, if we try to use it alone, at some point, if we lower reliability too much, you see with any of these curves, they all crash down to very low accuracy. So it's not a way to navigate the trade-off. So in addition to that, for example, you need to change the model size. If you're interested in going to lower energy and lower accuracy, you need to adjust your model size. So these are these additional curves where we additionally change the model size. Okay, and then we look at any given point, we look at what we can do at ISO accuracy and get pretty big energy gains. Okay, now I just wanted to give you a just overview of some recent work that we've done. So one is sharpness-aware training. So sharpness-aware training is definitely not our contribution. It was a different way to train models that with the objective of having better generalization and therefore just better performance on the test set, really. Okay, so the original idea of sharpness-aware training is summarized in this loss equation here. So what it says is that so usually when you would train the model, you would just be doing the minimization here. You're trying to find the weight value, right? That minimizes your loss on the the whatever loss function you have for training your model. But so what's added with sharpness aware is that you look at the loss not only at the weight W, but also in a neighborhood around the weight value. So intuitively, you can see this is going to also make your model more robust, because it means that if the weight changes a little bit, we hope to so what we're optimizing for is to still have a low loss value, even though there was this perturbation epsilon on the weight. Okay. And then there were some variations of this. One was adaptive sharpness, where it's exactly the same idea. It's just that the way we choose this epsilon that we optimize for, there's an additional normalization by the magnitude of the particular weight that we're looking at. And this helps become scale invariant to the different weight scaling that we can have, and ultimately allows to go for larger radius around the weights, to go for a smoother loss landscape at the end of the day. Okay, and our contribution here, it's called Samson, is again a different variation on this sharpness aware training, and we started working on it for model robustness, but actually also improved generalization. So we were pleasantly surprised with that. One advantage compared to other model robustness method is that you don't need to simulate the noise. You don't really need to know what the noise will be like on your hardware in order to train your model. Okay. And the loss function, again, it's the same. It looks a bit complicated, but essentially, if you remember the previous loss function, it's again similar. This is here the scaling that was from ASAM, and what we add is that this perturbation epsilon is then scaled positively by the outliers in the layer. So if the weight is if there's more outliers, we're going to go for larger neighborhoods, essentially. Okay. Okay, and it works really well. So we look at this again in the space of noise amount versus test accuracy, and this is the reference methods SGD. And just going to SAM and ASAM, SAM is the green line now, improves robustness. Sorry, going the wrong way. When we go, when we try our methods, it gives us even better robustness. And you can see we tried this on many networks, many data sets, including ImageNet, and the conclusions are always the same. And the cherry on top is what you see in the box here, is that even without noise, we get slightly better performance than the other sharpness-aware methods. Okay, so I'm going fast here. I'm probably out of time, right?
You still have a couple of minutes.
Yeah. Okay. So I'll go quickly on this. So that additionally to training the models, it's interesting to also have a method that allows us to, given a pre-trained model, we just want to know very quickly, is it going to perform well once we deploy it, for example, on a memristor, on a hardware that does its matrix vector multiplications with memristors, and maybe to optimize the hardware or to do various things. So this is just about characterizing the model. And so we developed a analytical method to do that, which allows us to go quickly. So the goal of the method is to measure the error between the noisy model and the nominal clean model that doesn't have noise. And we want this to be fast to evaluate. And because it's analytical, we could also, potentially use it in training, although we haven't so far been able to make successful use of it, but still working on it. But we have analytical equations, so they're differentiable and open the door to all kinds of gradient-based optimizations. So the model that we have, is the same as weights are represented as conductance values, and we add some noise to them. So there's target conductance, there could be quantization error, and then there's a variability due to the programming, so either write noise or read noise in the memristors. And as usual, there's a scaling factor that is just meant to adapt the weight to the range that we can represent on the memristor. And then we compare, standard DNN approach here. We just focus on the vector matrix multiplication. So in a standard DNN, we do the vector multiplication, gives us this equation. In a memristor, we split between positive weights and negative weights, so that splits the equation in two. And all both the weights or the conductance and the inputs become random variables. And we try to evaluate the error between the noisy output Z of any layer and the clean output, the small z. Okay. And here this box is that's not the clever part of the method. The clever part, or the non-trivial part, is in developing these equations to go through the entire model and to be able to predict what the error of each layer will be all the way to the output of the model. So on the experiments that we did, it works really well. So here we consider a small model, and we could see that there's excellent match between the theory and Monte Carlo simulations. So the analytical method really predicts the error very well. And here I add, so we have the MSE, and it correlates, as we might expect in a classification task, correlates with accuracy as well. There's two different curves. There's two different ways to map convolutions to memristors, but that's not really important now. Okay, and at the end of the day, it's much faster. So we compare, for example, we can take here the UR convolution mapping, and this is the amount of time it takes if we do Monte Carlo simulation, and the little blue bar here is what the amount of time it takes to run the analysis. So it can be much faster. So in conclusion, it's really crucial, I think, to develop robust DNN models if we want to fully address the energy efficiency of AI. And also, at the same time, when we develop these robust models, we also are protecting them against attacks. It's not always exactly the same problem, but it's very similar problems, so they can be really studied jointly. And then we saw that DNN architecture matters. So this is not something I talked about, but exploring robust DNN architectures is definitely interesting for future work. And different parts of the model are going to have different robustness to weight noise. And then once we train for robustness, we can get really big improvements in the performance of the model in noisy environments. And finally, we can develop analytical methods to characterize what happens and quickly be able to know if we reach the performance that our customer demands. Okay, thanks a lot. Sorry for being slightly over time.
Thank you, François. Great presentation, great insights. Do you have any quick questions before we dive into the panel session? I guess the panel session is a great opportunity to ask questions and discuss. So since we are running out of time, what about we jump to the panel session? So just share my screen. So I'll ask this is optional, by the way, for the presenters, but I ask all the presenters to enable your video and unmute yourself if you would like to participate. So we are a little bit behind schedule, 20 minutes, and we'll just make sure I have all the setup here. Great. And I encourage the attendees to either unmute yourself or ask question via the chat. Okay. So the objective of the panel session is to ask the following questions. So what do you see as the most important challenges and opportunities in cloud and edge computing? And I understand that some of the presentations already tackled these questions, but we'll go give each presenter 1 to 2 minutes to elaborate on these questions, and this will help CMC improve its current infrastructure to reduce these challenges and bridge the gap between different components. So as you see in this slide, CMC offers an advanced infrastructure that enables researchers to build, optimize, and deploy their deep learning models. On the cloud side, we have a variety of clusters that users access them specifically to train their model, including the FPGA GPU cluster, which has GPUs and FPGAs. We are currently upgrading this cluster with the latest software stack, and this will be available in the upcoming weeks. And we also have Atlas cluster, which is more for a high number of users that would like to accelerate their training on the neural processor units from Huawei. And on the optimization side, all the platform that we have support a complete software stack for optimization. On the deployments on the AI inference, we have a variety of platforms and IPs, including the one that is developed by Polytechnique that people can use and integrate in their platforms. So we would like to have a valuable feedback in order to improve the current infrastructure, and this is one of the most important elements of the workshop. So I will give each speaker 1 to 2 minutes to elaborate on these questions. So from your research perspective, what do you see as the most important challenges and opportunities in cloud and edge computing? Okay, so let's go with the order I have here. What about you, Francois? Just at high level, sure. From your research perspective, what do you see?
Well, I want maybe to take the opportunity to talk about what Andreas brought up, which I agree with, is you know, how to maintain continuity in academic research team is definitely a challenge when we're working with to try to contribute to hardware platforms that have, you know, a very high level of complexity that is impossible to manage in a single academic team, or, you know, even a few students can definitely not handle the complexity of the final hardware platforms that our research is about, right? So even though clearly we end up doing research with you know, some hypotheses and focusing on a small portion of the problem, we don't really have a good path to have a proof of concepts outside of course, maybe, you know, industry collaborations. But and I was curious to hear maybe that more concretely, Andreas, if you have any ideas of how this continuity can be improved in Canada or through CMC or.
Thank you, Francois. I mean, I feel the weight too high on my shoulders right now, but let me offer you my perspective. It's not that I have solutions necessarily, but I'll be happy to work with anybody that's willing to listen. And I think this has to be a team effort. Let me first say that right now, my impression is that the Canadian landscape is such that it's all upon industry to support academic research to move forward. And I don't think that's fair. I don't think that's fair to us, and I don't think that's fair to industry. I mean, sorry, I don't mean to put words on the mouth of people, but why would NVIDIA be interested in supporting 2 students every year so I can train them and potentially do something like that? Or untethered AI. I mean, they're trying to stand on their feet. They have great hardware, whatever. That's not the primary goal, right? But what we need to create is we need to create something that's a bit more permanent that can sustain. So, I mean, Warren's doing great work. Everybody's doing great work. I'm learning stuff I haven't heard, so it's kind of interesting. The grass is always greener on the other side, but maybe we can knock on the door of existing institutions like SciFar and say, look, I mean, there's this other aspect here that you may want to support because it's, I mean, fine, it's not ML itself, but it's something, it's an essentially greenery. There is industry that has been around in Canada for years, but there's new industry too. Maybe there has to be some support here to have some continuity, and maybe we can enable people also to collaborate, right? It's because I don't know everything. I mean, most of the interesting stuff that we've done, I like to think, is because somebody else told us something. We had the chance of working with them. Anytime I had a chance to talk to NSEC or whoever, it's always this random person that wants money, of course. There's a dime a dozen. So the only thing that I found worked in the past is to get industry to support us in that effort. And maybe we can try that trick again. But I'm happy to work with anybody that wants to try that out.
So
yeah,
in mind maybe like some kind of shared hardware platforms that.
CMC is an agency that provides tools and services that are essential. What doesn't exist right now in Canada, I think, for researchers like yourself and I, is a mechanism to also support the human capital that's required, right? That's what it is, right? I cannot go to CMC and say, give me money to do research, right? And that's what I'm saying. So there needs to be something else. Also, I don't think that there is, I don't know, I mean, Yasin, you can comment on that. Let's say I want to build a small prototype of something, right? I want to build a small chip. I know CMC is taking most of the burden of that cost, but there's a significant cost that's going higher and higher, right? It boils down to money, I think, at the end.
Yes, absolutely. My short comment is, like, from my perspective, I'm leading the AI project and activity at CMC. What I'm trying to do is to build an ecosystem, Canadian ecosystem around AI hardware, because we are lagging on that. Right, so bring in you guys, you experts in the field in this workshop is one of the milestones, and we should build on that. So researchers, they don't only need infrastructure, they need these channels of communication with industry, collaborative projects, and support of students. We are drifting a little bit away from the panel, but I think this is a very good question, and it should be part of this. So going forward, we need to work together in order to set objectives on especially HQP, right? Because if we don't support them for the next 2 years, nobody will be able to develop AI models in the future. There is a lot of focus on software, but not too much on the hardware. This is the gap that we should fill as we speak.
Talking, but I want to say, let's not forget that CMC itself had a big challenge getting supported, right? At some point, you were supposed to shut down, right? So whoever has the ears of the people that make decisions, they're not focusing on this stuff, right? We're not that important, I guess. That's what it is. Somebody else has the ears of the government or whoever makes the funding decisions.
I completely agree with you. I'm not very active on the funding side, but I know there is a great amount of work in progress in order to secure the next generation of HQP, and there is a proposal that CMC is working on that I mentioned in the presentation called Fabric, which is one of the objectives is what you are talking about as we speak. So I hope there will be continuity in that, and as CMC is always going through funding cycles, I am sure they will pull it out this time too. So let's keep with the same question. Warren, do you have any feedback on the questions or on your recommendation going forward?
Yes, first of all, I wanted to say that, from what Andreas and Francois were mentioning, so I'd be very happy to work with everybody on such an initiative. I think it's you hit the nail on the head there. So if you don't mind, I actually prepared a couple of short slides to talk about the challenges and opportunities. So I'll just share my screen.
Sure. Yes.
Just a couple, not a whole other talk.
Yeah.
Let me just find. I think it's here. Do you see my title slide?
Yes.
Okay, great. Okay. So most important challenges and opportunities. So imagine we want to, have a conversation with an AI, a conversation with a robot, for example. So I think over the past couple of months, the need for this, the use case has become incredibly sharp, right? We've seen ChatGPT, the incredible explosion of large language models into the public consciousness, right? So, what if we want to do that in real time? So, to illustrate, how this might work, I actually asked ChatGPT a question. What do you see as the most important challenges and opportunities in AI acceleration from the cloud to the edge, right? So let's see what it told me. So here it is. And it came up with some, coherent sounding answer. We don't need to read it. It's okay. It talks about the kind of things we talked about today in the workshop: CPUs, GPUs, FPGAs, ASICs. It talked about latency. It talked about privacy, all these things. Okay, very good. That's not why I brought this up. Can you see it? I'm sure we've all had this experience when using ChatGPT, the lag in the answer. So if you want to have a real-time conversation with it, is it fast enough? Now, keeping in mind that it's running in the cloud right now, but, what happened? I'm going backwards. What happens if we want to then put this onto edge devices, say to do real-time translation? Will this technology be suited? The challenge here is how do you put this into a phone, right?
Absolutely.
And so, to see the challenge that we're facing, here's a picture of some of the sizes of large language models, and you see out here is this GPT-4, which is officially undisclosed, but rumor is it's a trillion parameters, right? It's huge. And so the challenge: how do you fit these huge language models onto edge devices? The challenges, of course, are while retaining accuracy, acceptable latency, and energy consumption, and also, is it possible to learn or in the case of these modules, often fine-tune these on device? Also, the issue of safety. If you don't have supervision from the cloud, how do you ensure that you can use these in a safe way? And in following up on what was mentioned earlier by Francois and Andreas, I think it's becoming a big problem that we don't have the resources in a university or even SMEs to implement these kinds of models on our own. And so this is something I think we need to think about and come up with creative solutions. So I guess, okay, that's what I had. I'll stop sharing.
Thank you for the slides, Warren. This was very insightful. I just had a comment from Professor Yvonne Savaria, who said, "I am willing to contribute to any structuring initiative. If something gets initiated, so you know how to reach me." And he mentioned that he liked the workshop, so this is good. So, yeah, I think we'll just give Nizar a chance to give his comments, then we can discuss afterward. Nizar, what do you think, from your perspective? You've been doing research for a long time, working on very strong projects. From your perspective, what do you see as challenges and opportunities in cloud and edge computing?
I mean, I guess like large language models are the hot topic right now, but they are not the only topic out there. There's still a lot of work being done in different areas like computer vision and molecular biology and drug testing, and there are so many different stuff you can do with AI. But if I have to cite a challenge, I guess collaboration is a bit of a challenge right now because everyone's competing as a researcher to publish like as soon as possible, and trying to compete with other groups tends to be the way, to be the first one to get to the publication. And there's also like a challenge when it comes to fabrication. Let's say if you are doing hardware stuff, a lot of time you don't have access to be able to fabricate stuff. In our case, there are someone who's fitting the bill to fabricate, but I think like for a lot of research groups in Canada, this is a huge challenge. Like first to be able to access some of the technologies to fabricate and access the tools. I guess the tools, like if you have the money, it's no problem, but there's also always the issue of money. So having access to be able to fabricate stuff is a very difficult task. And also like retainment of researchers, like usually like most of the research is being done by like a group of students and postdocs, and so and these are only for a very short time, and then they have to leave, but then the project gets either delayed or just fall to other students. So this is also a huge challenge to overcome, like to be able to retain some talents to keep stuff going, to keep stuff because there is a big learning curve when you're jumping into a new project and trying to build either hardware or software techniques in order to accelerate some stuff on hardware. So I would say the challenges.
Yeah, thank you, Nizar. Any questions from the attendees to the panelists? Any additional comments from the speakers?
Well, Yasin, my suggestion would be if you have the time, maybe you can get us all together in a couple of weeks, in a week or so. So we can, because I only know so much, I only know so many doors to knock, right? Maybe others have other things. Maybe we can start creating some critical mass team that can go and knock on various doors and see which one opens, if any, right? To see. From my perspective, for the type of work, it's what Nizar just said, is I need access to technologies, I need access to ways to build small chips for prototyping. But that's what a small part. That's the continuity of support is much more important for everybody, I guess.
Absolutely, I agree with you. I will try to do that. Any other comments? So I think it's time to resume the workshop. In conclusion, we hope that Accelerating AI 2023 has been a valuable experience for all of our participants through engaging talks. So we have explored the latest trends and advancements in the field of AI implementation, optimization, and deployments. We have sent a survey to your email, so please take 2 minutes to provide us a quick feedback. This will help us improve our current events and products and services overall. And as we move forward, we encourage all of you to continue to build on the knowledge and insights gained during this workshop and to apply them to your own work. And we also invite you to stay engaged with CMC and the community through our different channels. So thank you for your participations, and we look forward to seeing you at Accelerating AI 2024. Thank you and have a wonderful day.
Okay. Thank you for organizing. Bye-bye.
Bye-bye.